Sometimes the things we feel most sure about are the ones that turn out to be the strangest. We grow up thinking of the universe like a big room we live inside, something with a somewhere and a someday, and then we find out that both of those ideas might be wrong. Space might not have an outside at all. Time might not have a clean beginning or a neat ending. The rules that feel obvious to us have surprised scientists over and over again. In this video, we'll sink deeper into that confusion and see what happens when you really take seriously the idea of edges, infinity, and the shape of everything. If you'd like more sleepy science videos like this, a gentle like really helps other people find them too, and get good sleep while learning. And I'd really appreciate a subscribe if you'd like to support more of them. Settle in for a moment with whatever you've brought into this night. Maybe you're already stretched out under something soft or curled on your side with the lights low. Maybe your room is almost dark or just bright enough that you can make out the outline of the furniture and the soft edges of the walls. Maybe there's a window slightly open and the air is a little cool on your skin. Wherever you are, this is a little pocket of time that doesn't ask anything from you. You don't have to be productive. You don't have to be alert. You don't even have to stay awake. This is a small, still space where science can move slowly and quietly, like a conversation happening in another room that you're only half listening to. This isn't a lesson. There's no quiz waiting at the end. We're just going to let some ideas drift past, unhurried ones. You don't need to grab hold of every detail. You're allowed to fade in and out, to miss whole pieces, to wake up later with only faint traces left, and still feel like something interesting brushed past your mind. That's perfectly fine. That's part of the design. Often, the most surprising thoughts don't arrive when we're concentrating hard. They sneak in when our shoulders have dropped, when our breathing is slow, when we're too relaxed to argue with them right away. That's a good state to think about something gently strange. Tonight, that something is a very old puzzle. It's the idea that the universe might go on without end, and yet somehow also have a kind of edge. At first, that sounds impossible. If something has no limit, how could there be any sort of border to it? Infinite sounds like it should mean no edges, no walls, no fences, no last step. It feels like one of those questions that's either too simple to bother asking or too tangled to ever really solve. But humans have never been very good at leaving questions alone, especially the slippery ones. And especially at night, when everything around us quiets down enough that the big questions can finally be heard. So we'll sit with it for a while, you and I, not to wrestle an answer out of it, but to see what's hiding inside the question itself. To notice what we really mean when we say words like infinite, or edge, or even universe. Sometimes just understanding the shape of a question is already a kind of answer. Before we drift too far into space, though, let's touch something simpler. Think, just for a second, about the time where you are. Not the number on the clock exactly, just the feeling of now, where you are lying or sitting. You're not only living in a place, you're living in a moment. This tiny slice of time sits in the middle of a huge stretch of history behind you and a huge unknown in front of you. And yet this little slice is the only one that feels real right now. No one else has this exact combination of you in this room, in this mood, on this night. While you listen, the universe hasn't paused. Galaxies are still slowly turning. New stars are lighting up for the first time. Comets are curving through dark space on paths they followed for millions of years. Whole clusters of galaxies are sliding farther apart. All of that is continuing, far away. But this small pause, this minute, belongs just to you. It's quiet in a very specific way, shaped by your breathing, your thoughts, your blankets, your room. That smallness doesn't make it less special. It makes it more personal. And as we talk softly about very big things, you don't have to do anything with them. You can just let your mind have something gentle to wander through while your body loosens and grows heavy. This is for curiosity and calm. It isn't meant to replace any kind of care or treatment you might need in real life. It's just a soft thread for your thoughts to follow, for as long as you're awake enough to follow it. If sleep comes in the middle, that's okay. The universe will keep on doing whatever it does, and the questions will still be there when you next feel like picking them up. So, we're already here, and the big question is already in the room with us. You don't have to do anything special now, just let your body be where it is, and let your mind wander a little. At some point in your life, maybe as a child, staring out of a window, or as an adult walking home at night, you've probably felt it. That little tug of curiosity about what's beyond all this, not just beyond your walls, or beyond your street, or beyond the last lights of your city, but the beyond that sits above the clouds, past the stars, outside of absolutely everything you know. It's the kind of beyond that telescopes chase. They point themselves into the dark and keep looking deeper and deeper, and it still feels like there's more. Like the picture never quite reaches the end of the page. You might have heard people talk about the edge of the universe and formed a picture without even meaning to. Maybe you imagine it like the edge of an old map, where the drawing just stops and something blank begins. Maybe in your mind it's a black wall, smooth and empty, or a glowing curtain, thin and strange, with nothing at all beyond it. You might picture a spaceship flying for an impossibly long time, farther than any human has ever gone, until one day it reaches that edge like the end of a highway. No more road. No more stars, just a choice. Turn around. Or try to push through. And then someone says, the universe might be infinite, and that whole picture dissolves. Infinite sounds like the opposite of an edge. If something is truly infinite, then surely there's no last step, no border, no final line where you can say this is it. Here it stops. That's the first part of the puzzle. Edges feel normal to us. We see them everywhere. Infinity, on the other hand, doesn't show up in ordinary life. You can imagine a huge number. Bigger than the number of people on Earth. Bigger than the number of grains of sand on every beach. But however big that number is, you can always add one more. It's still a number. It still sits somewhere on a line. Infinity isn't like that. It isn't the biggest number. It's not even a number at all. It's more like a direction you never finish walking in. A road with no last exit sign, a counting that never reaches a final. And that's all. So we end up with two ideas that don't seem to fit together. A universe that might be infinite, and a universe that might have some kind of edge. How can both pictures even live in the same mind? The honest answer is, we don't know for sure yet, but we do have ways to talk about it. We build mathematical models, soft frameworks of symbols and rules. We think philosophically about what words like space and limits really mean. We point our instruments at the sky and collect real data. Light, signals, patterns. Some of our ideas have been tested carefully. Others are still guesses we're trying to tame. All of them move around the same central mystery. What shape does the universe have? And if you know that shape, does it tell you whether it ends or never does? Even the phrase edge of the universe is slippery. We have to slow down and ask, which edge do we mean? Do we mean an edge of space? The furthest point you could travel to? If you had endless time and a very patient spaceship, always moving in one direction, never turning around? Or do we mean an edge of time? A first moment where everything begins, or a final moment where everything stops? Or are we secretly asking something simpler and stranger? Is there some place where things just stop existing? A cosmic wall, a border, a place where space itself runs out, and there literally is no further to go? Those are very different questions, hiding under the same word, edge. That's where we're heading tonight, slowly. We'll talk about shapes, but not just the kind you can draw on paper. We'll talk about how space can bend, and how that bending might let it be finite without having a wall. We'll talk about the universe expanding, and what that even means if there's no outside for it to grow into. We'll talk about horizons, not as lines you can touch, but as limits on what you can ever see or know. And we'll notice how our tiny, short lives, inside a brief moment of cosmic history, shape the way we ask all of this in the first place. To get ready for that, imagine something simple. Picture an endless landscape, perfectly flat, stretching out in every direction. You choose a direction and start walking in a straight line. You never get tired. You never turn. You never stop. What happens? Do you eventually run out of ground? Do you find a cliff with empty nothing below? Do you run into a wall, some final structure with a hard, absolute no farther stamped into it? Or do you just keep going, always finding more ground ahead of you? And here's a twist. What if, after an unimaginably long time, you somehow come back to the exact point where you started, without ever turning around? That would mean the ground itself was not what you thought. It would mean you'd been walking on a surface that loops back on itself. Not infinite in the simple way you imagined, but also without any edge to fall off. Something curved, not flat, even if it felt flat under your feet the whole way. Hold that picture for a moment. Now zoom all the way out. Replace that flat floor with space itself. Replace your footsteps with beams of light, or the motion of galaxies, or the paths drawn by gravity. What is the shape of that space? Is it truly flat, so that straight lines never meet again? Is it curved back on itself, like the surface of a giant sphere? Is it curved in the opposite way, like a saddle, flaring outward? Does it go on without looping? Or does it quietly wrap around in directions? Our brains aren't built to picture. We're getting close to those questions, but we don't have to answer any of them right away. Tonight isn't about racing to a conclusion. There's no scoreboard. It's more like taking a long, slow walk and noticing how the path feels under your feet. Infinity doesn't rush. It doesn't care how quickly you understand it. It just sits there, patient, whether you look at it or not. So, wherever you are, however your day has been, whatever thoughts are still buzzing around, let them drift to the edges a little. You don't have to fight them. Let them become a quiet background hum, like faint static behind the stars. We'll talk now, softly, about something very, very large. And we'll start with something small and familiar. A room. Imagine an ordinary room. 4 walls, a ceiling, a floor. You can stand up and walk until your hand presses against a surface. You know exactly where here ends. The space is closed, contained. The edges are solid and easy to find. Now imagine the walls quietly vanish. No crash, no drama. They're just gone. You're left standing on the same floor, but now it stretches out flat in every direction, with nothing to block your way. You pick a direction and start walking. No furniture to dodge, no doors, no corners, no cliffs. You don't get tired. Time doesn't feel normal. You're just moving. At some point you start to wonder, will something appear? Will there be a last step? Or will this flat floor, this simple space, just keep going forever? And what if, after an unthinkable distance, your next step brings you back to exactly where you began? You never turned around, you never changed direction, but somehow the path closed on itself. That would mean the space you trusted as flat wasn't flat after all. It would mean you'd been walking on the surface of something larger, something curved, without knowing it. That is the kind of question we'll keep circling gently tonight. Take that floor and upgrade it to a universe. Take those footsteps and turn them into light, gravity, galaxies. Ask again, what is the shape of space? Does it have to end to be finite? Does it need an edge to be real? Can something have no wall and still not be truly infinite? We're not searching for a finish line. We're just walking and talking and asking quietly. And as we go, the words infinity and edge might start to feel a little different than they did before. Try, just for a moment, to imagine the shape of something that isn't moving. Not the shape of a chair, or a cup, or a mountain, but the shape of stillness itself. At first, that sounds wrong. Shape makes us think of outlines, edges, corners. Stillness makes us think of nothing happening. No motion, no change, no flow, just a moment held in place. But if we're talking about the universe and about space itself, then even the calm has a structure. Even when nothing obvious is happening, space is still there, quietly holding its own form. Too big to sketch, too slow to feel, too gentle to notice day to day, but it has a shape all the same. When most people picture space, they imagine it as basically flat. Not flat, like a sheet of paper lying on a desk. Exactly, but flat in the way school geometry feels flat. Lines go straight and stay straight. Parallel lines never meet. If you draw a triangle, its angles add up to 180 degrees every time. If you walk in a straight line, you never secretly curve back to where you started. That's the kind of space we're used to. Predictable. Comfortable. Comfortable. Distances behave the way your instincts expect. But the universe doesn't have to follow those simple rules everywhere. Once you stop looking at local neighborhoods and start asking about all of space at once, the picture can change. Go back to that endless, featureless landscape. You pick a direction. You walk in a perfectly straight line, as carefully as you can. No turns. No detours. No hills to trick you. If space is truly flat and truly infinite, then you just keep going. You pass new ground again and again. You never loop back. You never see the same patch twice. Your journey is always forward. But if space is curved, even a little, something more surprising can happen. You can keep walking in what feels like a straight line forever and eventually arrive back where you started. Not because you turned around, but because the space beneath your feet has curved around behind you. In that kind of universe, the paths things can take are shaped by the space itself. It might have no center. It might have no edge, but it still has a geometry, a quiet rulebook that tells lines how to behave and motion how to unfold. A favorite way to picture this is the surface of a sphere. Think of the skin of a balloon. If you're a tiny creature walking on that surface, it feels flat where you stand. You can walk in what you call a straight line, in any direction. But if you keep going long enough, you eventually end up back where you started. You never find a cliff. You never hit a wall. The surface has no edge, but it's not infinite either. There's only a certain amount of area. From your point of view, the horizon always just sits a little way ahead of you, no matter where you go. That's only a picture, though. Our real universe, as far as we know, doesn't have just two directions on its surface. It has three spatial directions to move in: forward and back, left and right, up and down. If those three directions are curved, they curve in a way that's hard to imagine. They don't bend into a fourth classroom direction, like up on a blackboard. They bend in a higher dimensional sense, one our brains aren't built to see directly. We can write the math for it. We can put it into equations, plot pieces of it on graphs, let computers simulate how things move inside it. But we can't hold the whole shape in our mental hands the way we can hold a globe or a map. It's too big and too abstract for a simple picture. Even so, that shape is there. It's not just decoration. It decides how galaxies drift apart. It decides how light curves near massive objects. It decides how the tiny ripples from the early universe spread out after the Big Bang. In that sense, the shape of stillness is like the stage of a theater. We pay attention to the actors, stars, planets, galaxies, explosions, but the stage beneath them quietly decides where they can walk and how far they can go. We usually ignore it because it's not moving, but without it, nothing else would move the way it does. So what do we actually know about this stage? Not everything, but more than we used to. When astronomers look into the sky, they can see a faint glow coming from every direction. It's not starlight. It's older than any star. It's the leftover warmth from when the universe was young and hot and dense. We call it the cosmic microwave background, the afterglow of the Big Bang, slowly cooled. If you map that glow very carefully, you find that it isn't perfectly smooth. There are tiny variations, tiny spots that are a little warmer or cooler. Those tiny bumps and ripples carry clues about the shape of space itself. By measuring how those patterns are spread across the sky, we can test what kind of geometry fits them best. Is space curved inward, like a sphere, curved outward like a saddle, or very close to flat? So far, all the measurements say it's extremely close to flat. If there is a big curve, it's gentle enough that we haven't detected it yet. On the scales we can observe, space behaves as if triangles really do add up to 180 degrees, and straight lines don't naturally loop. That sounds like it might mean space goes on forever in all directions. And it could mean that a perfectly flat universe can be infinite, but there's another possibility. Space might be curved or wrapped in a way that happens so slowly, over such enormous distances, that our part of it looks flat, like standing on a huge sphere and only seeing a tiny patch. Your small area looks straight, even though the whole thing is round. That leads to something important. We don't see the entire universe, we see the observable universe, just the region from which light has had enough time to reach us since the beginning. Everything farther away than that hasn't had time to show itself yet. Not because it's hidden behind anything, but because light, even at its speed, has only had a limited number of years to travel. And because space itself is expanding, some of that distant light may never get here at all. So when we say the universe looks flat, what we really mean is the part we can see looks flat. Maybe that flatness continues forever in every direction. Maybe we really do live in an infinite, edgeless space that never loops back. Or maybe our visible patch is just one small tile in a much larger curved shape. We might be mistaking a tiny bit of a big curve for a straight line, simply because we can't see the rest of the arc. In that second case, the universe could still be finite in total size. It could wrap around on itself in some higher dimensional way we can't picture clearly. You could, in theory, travel straight and eventually come back to where you began, not because you turned, but because space closed the loop. If that's true, then there's still no edge. You never meet a wall. You never hit a border where space ends. But it also wouldn't be infinite in the usual sense. It would be edgeless and bounded at the same time. That's where things start to feel slippery. How do you even measure something like that? What does it mean to talk about the size of space when space is also the thing that defines what size is? From inside the universe, which is the only place we can be, we use space to measure space. We stretch out rulers. We time how long light takes to travel a distance. We compare the gaps between galaxies, but we can't step outside and look back at the whole thing from above. There is no above. The universe isn't sitting in a bigger room. It is the room, so we work from within. We collect data. We map what we can see. We test shapes and models against the patterns in the sky. We try to infer the whole structure from a limited view, like trying to figure out the shape of a huge object by feeling only a small part of it in the dark. Even if we never know the full outline, the idea of shape still matters. It matters because the geometry tells us how the universe behaves. If space is positively curved, like a sphere, light paths can eventually loop back. Parallel lines may meet. If space is negatively curved, like a saddle, light rays tend to spread apart more than they would in flat space. Triangles have angles that add up to less than 180 degrees. If space is flat, light travels in what we call straight lines. At least straight with respect to that geometry. Parallel lines stay parallel. Things behave in the way your school diagrams suggested. On the scale of rooms and cities and even planets, these differences are too subtle to notice. The universe is so big that any curvature is smeared out over unimaginable distances, but on cosmic scales, those tiny differences add up. They change how the universe expands. They affect whether it might one day slow and collapse or keep spreading out forever. They influence how structures form, how galaxies cluster, how gravity shapes the web of matter. Through it all, the shape is always there. Even when everything looks still, even when galaxies drift so slowly across the sky that you'll never see them move in your lifetime. Even when the night above your house looks identical, night after night, the geometry of space is silently present in every quiet moment. It cradles the apparent stillness. It decides what straight ahead really means. And somewhere inside that structure may be the answer to our old question. Because if space has a particular shape, curved, flat, or something stranger, that shape might tell us whether an edge is even a sensible thing to look for. So far, we've seen no sign of a wall. No hint of a border where space just stops. What we have seen is pattern and structure and rules that seem to hold everywhere we can look. That hidden geometry, the shape of stillness itself, might be the key to understanding how we can move through something that may not end, and still find ourselves wondering where, exactly, it begins. Let's slow down with that little word, edge. We meet it early in life, the edge of the table, where your hand can slide no farther. The edge of a book, where the pages and the story stop. The edge of a cliff, where ground turns into air and then into a long drop. An edge is where something ends and something else begins. Inside is the thing. Outside is not the thing. It's a clean idea, clear lines, clear borders. Edges help us feel oriented. They let us say, this is part of it, that is not. We talk about edges all the time without noticing. The edge of the city where buildings fade into fields, the edge of the forest where trees thin out and sky opens, even the edge of an idea where what you understand fades into a soft blur of I'm not sure. So when we ask, does the universe have an edge? It feels like the same kind of question, but it isn't. We're not talking about the edge of a table. We're asking if everything, all space, all time, all matter, all light, could somehow have a border. And if it does, what's on the other side of that border? And if it doesn't, how do we even think about that? It's hard to picture something that includes absolutely everything and still has an outside. Outside always suggests more space. Another room, another field, more air. But if the universe already contains all space, then there isn't room for an outside. An edge in that context would be a line beyond which there is what? Not space, not time. Not even empty vacuum, because even emptiness is a kind of space. So what's left? A kind of non-place where going somewhere simply stops making sense. That's where our usual idea of an edge starts to crack. Because physically, an edge is defined by what's on the other side. A book ends where the air begins. A sidewalk ends where the street starts. The contrast makes the edge real. But the universe isn't sitting on something. It's not laid on top of a bigger background. It is the background. It's the setting in which everything else sits. So when we talk about an edge of the universe, we're really asking one of two things. First, is there some distance beyond which space itself simply doesn't continue? A true outer limit where there are no more points, no more directions, no more over there at all? Or second, is there some deep kind of transition? A region where the basic rules change, where the structure of reality, or the values of the fundamental constants, or even the number of dimensions, are not the same as here. That second kind of edge is softer. Not a wall you bump into, but a threshold. You might not see it or feel it as you cross, but beyond some distance, reality itself might be different. Some theories hint at things like that. Certain versions of cosmic inflation, the idea that the early universe expanded incredibly fast, suggest that our whole observable universe might be just one bubble inside a much larger multiverse. Each bubble could have its own version of physics. Slightly different numbers, different particles, maybe even different dimensionality. In that picture, there is a kind of edge, not a solid wall but the boundary between bubbles, where one universe ends and another begins. But so far that's theory. not measurement. We have no direct evidence yet. There's another quiet assumption hiding in the word edge. Most people imagine it as a location you could go to. You travel far enough, you reach the end, you stand there and look out over the side at something. Or nothing. Or a big black void. That picture treats space like a fixed landscape, a floor you can walk across, a map you can trace with your finger. But real space isn't just a static surface. It curves, it stretches, it changes over time. It's part of the physical system, not a stage that sits still while everything else moves. To untangle this a bit, imagine something simpler, a video game world. Forget the characters on the screen for a moment and think about the world underneath, the rules that define it. In one game, the world might be a huge square. You walk to the edge, and your character pushes against an invisible barrier. No matter how hard you try, you can't go farther. Nothing exists beyond that line. The developers simply didn't create anything there. That's one kind of edge, a hard limit. The world ends, and there is literally no beyond inside the game. In another game, you might walk east for a long time, and eventually your character appears again on the west side of the map. You've wrapped around, no wall, no cliff, just a looping world. You can keep walking forever, but you're really revisiting the same space again and again. That's a different kind of edge, not a stopping point, but a connection. It's not infinite, but it doesn't present you with a final boundary either. In yet another game, the world might generate itself as you explore. New terrain appears only when you walk toward it. From inside the game, it feels endless. You can keep going and always find more. But from outside, from the programmer's viewpoint, it's still limited. It only exists where you've been plus, where the code will allow it to grow. Now bring those ideas back to our universe. We don't yet know if the universe is programmed like that first example, with an absolute outer limit. We don't know if it loops like the second, folding back on itself. We don't know if new regions of space come into play the way the third game generates terrain, as expansion unfolds. What we do know, from where we sit, is that we haven't found a barrier. Light reaches us from billions of light years away. In every direction, as far as our instruments can reach, space continues. But our view is not infinite. The speed of light sets us a horizon, a maximum distance we can see. Not because there's a wall there, but because light from beyond that distance simply hasn't had enough time to arrive. We call the region. We can see the observable universe. It's like standing in a thick fog. You can only see a certain distance before the view fades out. The world doesn't necessarily end where your sight stops. Your vision does. That foggy edge, the observable horizon, is often mistaken for a real boundary. It isn't. It's just the limit set by time and light. The universe might stretch far beyond it. It might go on forever. It might loop back in some complicated way. It might even stop not far beyond what we see. Right now, we don't know. There's another kind of limit, though, that's especially important. Because the universe is expanding, and because distant regions are being carried away from us by that expansion, there's a distance beyond which things recede faster than light can bridge the gap. Not because those galaxies are breaking the speed limit, but because the space between us and them is swelling so quickly. That creates a different horizon, a cosmic event horizon. Beyond that, even if you had all the time in the world and could travel at light speed, you'd never reach those regions. They're not just unseen, they're forever unreachable. No signal from us can ever get there, and no signal from there will ever reach us once they're beyond that line. That's another kind of edge. Not a place in space, but a limit on contact. A boundary on what can ever be known or influenced. And even that edge moves. The observable universe grows as more light arrives with time. The reachable region changes as expansion continues. The edge is not a fixed location waiting for you to discover it. It's something that depends on the rules of the universe and where and when you're looking from. So when you lie there and wonder, Does the universe have an edge? The answer quietly turns into another question. Which kind of edge do you mean? If you mean a physical wall where space literally stops, we haven't seen anything like that. If you mean a limit to what we can see, then yes, there is a horizon, but it isn't a solid border. If you mean a deep change in the nature of reality, a region where the rules themselves are different, that's a maybe, a possibility we don't yet have proof for. The most useful way to think about the word edge might not be as a place at all. Maybe it's better to think of it as a relationship. A relationship between what's known and what isn't. Between what can ever affect us and what never will. Between what fits inside our measurements and what stays forever beyond them. That's what makes the question rich, instead of empty. It's not really about finding a giant cosmic wall. It's about understanding what it means to hit a limit, and what might live just past the edge of our knowing. And to go any further, we have to talk about one of the trickiest ideas of all. Infinity. Infinity sounds like a big dramatic word, but what is it actually pointing at? How is it different from just really, really large? And is it possible for something to be infinite and still not have an edge, or to have no edge and still not be infinite? Infinity isn't a number in the usual sense. We talk like it is. We say things take forever, or that there are infinite possibilities, or that the universe might be infinitely big. In everyday speech, we mostly mean so much I can't really imagine it. A lot. Too many to count. Bigger than feels comfortable. But in science and in math, infinity is something different. It doesn't live on the normal list of numbers. You can't get to it by counting. One more, and one more, and one more. You can't reach it by writing more zeros on the end of a number. That's still just a number with a name, even if it's huge. If you push your calculator too far, it might give you an error message or a little kind symbol. But infinity isn't the calculator's biggest number. It's not a mistake, it's an idea. This doesn't stop. Infinity is what you mean when you say, there's no end to this pattern. It doesn't describe a particular amount. It describes behavior. Something is infinite when there's no final step, no last point, no now we're done. In math, you might see a phrase like as x approaches infinity. That doesn't mean x ever becomes infinity. It means x can get larger and larger without any upper limit. The process is the key. You never arrive. Infinity is the direction the sequence is heading, not the destination it reaches. In real life, we're not surrounded by actual infinities. We see big and small, but always with limits. The sky feels endless, but it's filled with stars and galaxies we can count and measure if we have enough time and tools. The ocean seems to go on forever when you stare at the horizon, but it has shores and depths and a bottom. So when scientists say, maybe the universe is infinite, they're not saying we've measured how big it is, and the answer is a special number called infinity. They're making a statement about structure. They're saying, as far as we can tell, there's no sign of a boundary, no sign of folding back, no hint that space stops. The geometry we see would allow space to just keep going. An infinite universe doesn't mean it contains every possible thing you can dream up. It doesn't automatically mean every story happens somewhere, or that every choice is replayed in another corner. It simply means the fabric of space might extend without limit, so that you could travel in a straight line forever and never loop around, never crash into a wall, never find a last star. But here's the subtle twist. You can have something with no edge that still isn't infinite. Think again of the surface of a sphere, like the skin of a planet or a balloon. There's only so much area. You can measure it. It's finite. But from the point of view of a tiny person walking around on that surface, there's no edge. You can walk in any direction indefinitely and never fall off. You might circle the globe many times, but you never find a boundary that says end. That's a finite space with no edges. Now imagine that idea in more dimensions, a three-dimensional universe that wraps around on itself in a way we can't easily picture. It could have a limited total volume, a definite amount of space, and still feel boundless from the inside. You'd never stumble into a cosmic wall. You just keep going, over and over, always moving forward, and eventually coming back to where you started. That's different from an infinite universe. One loops, the other doesn't, but from a traveler's point of view, both feel edgeless. This is why it's important not to mix up no edge with infinite. You can have one without the other. A space can be finite and still never give you a wall, and a space can be infinite without containing every story your imagination can invent. So how do scientists even start to figure out whether the universe is infinite? They look for clues in how space behaves, how light travels, how galaxies are spread, how the cosmic background glow is patterned. Right now, all those clues suggest that on very large scales, space is flat or extremely close to flat. If it's exactly flat and doesn't loop back on itself in some clever way, then the simplest conclusion is that it's infinite. Not because we've checked every corner, but because the geometry doesn't naturally fold, it just keeps going. But we have to remember, we're only seeing a portion. The observable universe is like a giant bubble centered on us, about 93 billion light-years across from one side to the other. That number sounds bigger than big, but it's not the age of the universe times the speed of light in a simple straight line. Space has been expanding the whole time light was traveling, so the edge of what we can see is farther away now than the raw age would suggest. Even then, that distance is not an edge of reality. It's just a horizon, a limit set by how long light has been on the road. Beyond that horizon, space continues. We just haven't heard from it yet. What's out there could be part of an infinite universe, or part of a finite, looping one. Right now, there's no way to tell. For many people, infinity feels uncomfortable because it doesn't behave like anything familiar. It feels too big, too slippery, too abstract. But you don't have to picture all of it at once. You can think of it more gently, as openness. A system without walls, a space where there is always more space. That's enough to work with. And it's worth clearing up another confusion. Infinity doesn't mean anything goes. An infinite universe can still be orderly. It can still follow strict rules. It can still have laws of physics that never change. Infinity doesn't erase structure. It just removes the fence at the edge. In fact, in mathematics, even infinity itself comes in different sizes, which sounds impossible at first. The set of counting numbers, 1, 2, 3, 4, and so on, is infinite. So is the set of all real numbers between 0 and 1. But there are more numbers in that tiny interval from 0 to 1 than there are counting numbers altogether. Both sets are unending, but one is larger in a precise mathematical sense. Those ideas are useful for mathematicians when they think about sets and continuity and limits. In physics, we care less about comparing different infinities and more about what an infinite or finite universe would mean for us, where we sit, what we can see, what the long-term future might look like, how space and time are shaped. If the universe really is infinite, then our observable patch, that 93 billion light-year bubble, is just a tiny island in an ocean of space that has no shore. Our whole sky, everything we'll ever see, would be only one region among endlessly many. That raises more questions. Are the laws of physics the same everywhere, all the way out? Is matter spread in roughly the same way, with galaxies and clusters and voids? Or are there regions so different we wouldn't recognize them at all? We don't know. We can make an educated guess from what we can see. On very large scales, the universe looks surprisingly uniform. That suggests that our patch is not special, that the same patterns continue and the same rules hold far beyond our horizon, but we can't test that directly. No telescope will ever let us reach past the speed of light. So in our models, infinity is a kind of stand-in. It means we don't see a boundary, and the equations don't demand one. It doesn't prove that a boundary is impossible. It just says we haven't found it, and we don't currently need it to explain what we observe. And that loops us gently back to edges. If the universe is infinite, then by definition there's no outer edge. But if the universe is finite and unbounded, if it loops or wraps around, then there's also no edge, no wall, no border, no last stop. In both cases, strange as it sounds, we end up in the same place. The universe might have no edge, whether it's infinite or not. That's the part people often miss. No edge doesn't prove infinity. Infinity doesn't automatically remove any kind of boundary. Everything depends on the shape of space, on its deep structure, on the geometry tying it all together. So maybe the most useful question isn't, is the universe infinite? Maybe a better question is, what is the shape of the space we live in? How does it curve? How does it connect to itself? How does it guide the paths of light, the motion of galaxies, the flow of time? Those are questions we can actually begin to answer. Not by hunting for cosmic walls, but by watching how things move, how patterns of radiation spread, how gravity bends the paths of light across the sky. If you've spent any time with space documentaries or books, there's a good chance you've met the balloon. Not because anyone thinks the universe is literally a big rubber ball floating in the air, but because balloons give us a surprisingly gentle way to picture something that would otherwise twist our brains into knots. It's not a perfect picture. It's not meant to be. It's just a little doorway into an idea. The story usually begins like this. Imagine a balloon. And now imagine drawing tiny dots on its surface with a pen. Each dot stands for a galaxy. Now you start to blow the balloon up. As it inflates, the dots move farther apart from each other. Not because the dots decide to slide along the surface, but because the surface itself is stretching. There's more space between each dot, even though the dots are just sitting where they are. That's the key idea. The space between them grows. In the real universe, it's a bit like that. Galaxies aren't all flying away from each other like shrapnel from an explosion. For the most part, they sit in their own regions, held together by gravity. What changes is the distance between those regions. Space itself stretches, and as it does, the galaxies drift farther apart. In the balloon picture, the surface of the balloon is what represents space, not the air inside. Not the rubber as a whole, just that thin two-dimensional surface. That surface has no edge. If you were a tiny creature stuck to it, you could walk in any direction as far as you like. You'd never find a cliff, you'd never fall off. You might circle around and end up where you started, but you'd never hit a boundary. So the surface is finite. It has a limited area, but it's still edgeless. No walls, no borders, just a continuous curve. That's why the balloon is so useful. It shows how something can be limited in size and yet have no outside edge for you to bang into. You can move forever and always stay inside the same space. As the balloon keeps inflating, every point on the surface moves away from every other point. And here's a subtle but important detail. There is no special dot on the surface that counts as the center of the expansion. From any dot's point of view, all the other dots seem to be receding. Everywhere looks like the middle. The actual center of the balloon's expansion isn't on the surface at all. It's in the space outside, in the three-dimensional world we're using to imagine this two-dimensional skin. But the little creatures living on the surface don't have access to that. As far as they're concerned, there is no up and out. There's only along the surface. From their perspective, the expansion looks the same from every point, in every direction. That's the first thing people often get wrong when they hear this metaphor. They try to find the center on the surface, but there isn't one. The second mistake is imagining the expansion as the surface pushing into some surrounding emptiness. From our point of view, yes, the balloon grows into the air, but from the point of view of a creature living only on the surface, there is no outside air at all. There's just more surface, more space between things. Now take that idea and bump it up a dimension. Instead of a two-dimensional surface, think about our three-dimensional space: forward, backward, left, right, up, down. The expansion we observe in the universe isn't galaxies racing through some pre-existing void. It's space itself stretching, The distances between galaxies are increasing over time, the same way the distances between dots on the balloon grow. Your room doesn't expand. Your body doesn't slowly stretch as the universe ages. The Earth stays held together. The solar system remains bound. On those scales, gravity and other forces are strong enough to ignore the stretching. It's only when you look at vast distances between galaxies and clusters of galaxies that expansion shows up, and the farther away something is, the faster it seems to be receding. Not because it's zooming away under its own power, but because there's more and more expanding space between you and it. The balloon is still only a picture. The universe is not a balloon's surface. Our space has 3 dimensions, not 2. And we don't have any clear evidence that it's sitting inside some larger, higher dimensional room in the way the balloon sits in the air. If space is curved, that curvature happens within the universe's own structure, not into some surrounding superspace. There is no container we can point to and say, that's what the universe is expanding into. People asked, quite naturally, if the universe is expanding, what is it expanding into? The quiet answer is, nothing. Expansion doesn't need an outside. It simply means that the distances between points in space are increasing with time. The grid itself is stretching. In a room, you can describe where you are by measuring from the walls or from a corner. In space, we don't have those outer walls, so we describe positions by how far things are from each other. This galaxy is so many light years from that one. When the universe expands, those distances grow, not because galaxies are flying outward into a larger arena, but because the measuring stick between them is stretching. The coordinates themselves are changing. That's why the balloon example is most helpful. If you imagine living on the surface, not outside staring at it. From the surface creature's point of view, there's no edge to hit, no center to find, just an ever-growing distance to everything else. Look around, and every other point seems to drift away from you as the balloon inflates. If you move to any other dot, you'd see the same thing there. Now apply that thinking to our own universe. We look out with our telescopes and see galaxies moving away from us. And the farther they are, the faster they seem to recede. It's tempting to think, so clearly we're at the center. But if you were standing in a galaxy 1 billion light years away, you would see the same pattern from there. Everything else would seem to move away from you. There's nothing special about our location. Expansion looks the same from anywhere. This idea that the universe looks similar on large scales, no matter where you are and no matter which direction you look, is called the cosmological principle. Homogeneous, roughly the same everywhere, isotropic, roughly the same in every direction. No central throne, no favored direction. Just one vast expanding space where the rules are shared. That might sound abstract, but it has real consequences. Because if the universe looks the same in all directions, then the light we see from distant galaxies and the faint microwave glow from the early universe aren't just local quirks. They're telling us about how space itself behaves, about the geometry that underlies expansion. And when we use those observations to test our models, we find that the geometry of space is, as far as we can measure, very close to flat. That doesn't mean it's literally like a tabletop. It means that on large scales, light travels in straight lines, the way we expect from normal geometry, and the angles of big cosmic triangles behave as they should. If there is curvature, it's very gentle. So gentle that across billions of light years we still haven't clearly seen it. The balloon's surface is an example of positive curvature. It wraps in on itself. A saddle shape is an example of negative curvature. It bends outward in different directions. Our universe seems to be somewhere in between those extremes, so close to flat that, from our vantage point, we don't see obvious looping or distortion over cosmic distances. That doesn't mean the balloon picture is wrong. It just means it's one particular possibility. If the universe is positively curved, it could indeed be finite and unbounded like the balloon's surface. If the universe is perfectly flat and endless, then the balloon metaphor breaks at that point. There's no looping back, just unending space, but the metaphor still does two very important jobs. First, it reminds us that you can have a space with no edge, whether it's finite or infinite. A balloon's surface is finite, with no boundary. An infinite flat plane also has no edge. The absence of a wall doesn't tell you which one you're in. Second, it shows us that expansion doesn't need a bigger room. The container is space itself. It can grow not by adding new outer layers, but by stretching the distances inside. So when you hear that the universe is expanding, try not to picture a ball swelling inside a larger empty box. Instead, picture the distances between everything quietly increasing from within, the way the balloon's surface grows in all directions at once, from every point, without needing any outside to grow into. The space itself becomes more spacious. And now that we've played with that image for a while, we can start peeling the metaphor away and ask a more precise question. If space expands this way, stretching, maybe looping, maybe not, what does that tell us about its true shape? Can we put a name to that geometry? Can we predict how it will behave in the long run? That's where we leave rubber balloons behind and step fully into geometry. By now we've played with words like flat and spherical and saddle-shaped, as if the universe were a kind of giant object we could hold up and inspect. But underneath those pictures, there's something deeper going on. The universe doesn't just have a shape, it has a structure. A geometry. That geometry quietly decides how things move, how paths bend, how light travels, how gravity pulls. It's like the rule book for motion, written into space itself. We've already talked about space stretching, about light crossing an expanding fabric, about balloons and infinity, and the idea that you don't actually need an edge for a universe to make sense. But there's a more precise way scientists talk about all of this. They ask a question they keep coming back to again and again. Is space flat, open, or closed? Those words aren't just labels from a textbook. They're three different ways the large-scale universe might be arranged. Three different global shapes for the stage everything plays out on. We're used to curves in everyday life. Roads bending around hills, domes on buildings, the roundness of the earth. But cosmic geometry is not the curve of a mountain or a road. It's the way the entire universe bends. The way it shapes time, the way it guides light, the way it sets the long-term fate of everything inside it. Let's start with the one that feels most familiar. Flat. When cosmologists say the universe is flat, they don't mean it's a thin sheet floating somewhere, like a giant piece of paper. They mean that on large scales, space follows the same geometric rules you learned in school. Parallel lines stay parallel. Triangles have angles that add up to 180 degrees. Light rays, if nothing heavy is nearby to bend them, move in straight lines. In a flat universe, space doesn't curve inward or outward on its own. It can still expand. It absolutely does. But that expansion doesn't naturally fold back around or flare out like a saddle. It's neutral. Balanced. In that simple picture, flat space tends to be infinite, unless something special happens to connect it back on itself. You can keep zooming out, and it looks the same. No global bend, just more of the same kind of grid extending in every direction. Now imagine the closed case. Here, space curves inward, somewhat like the surface of a sphere. Not a ball in space, but space itself having the same kind of inward bend. A three-dimensional world that curves in a higher dimension. This is harder to see in your mind, because we don't walk around inside naturally looping three-dimensional spaces, but the key idea is simple. In a closed universe, if you pick a direction and travel straight long enough, you eventually come back to where you started. You never turn around. You never aim yourself backwards. The space itself just curves your path into a loop. This kind of universe has a finite volume. There is only so much space in total. But there is still no edge, no blank wall, no outside. You can move forever and never fall off, because the space connects back to itself. It's like living on the surface of a planet. You can walk in circles around it for as long as you like, and never find a border you can fall past. The world feels unbounded, even though it's limited in size. A closed universe also carries a hint about its possible future. Like all models, it starts with something like a big bang, a hot, dense beginning, where everything is closer together. But in a closed, positively curved universe, gravity on very large scales can be strong enough to eventually slow the expansion, stop it, and then reverse it. Instead of expanding forever, the universe could someday begin to contract. Galaxies would drift closer together. Distances would shrink. In the end, everything could collapse back into a dense, hot state, a big crunch. Not guaranteed, but it's a natural storyline that goes with this kind of curvature. Now the third option, open. An open universe curves the opposite way, outward, like a saddle. It doesn't close on itself. You can travel straight forever and never return to your starting point. In this geometry, parallel lines tend to drift apart. If you draw a triangle on a large enough scale, the sum of its angles adds up to less than 180 degrees. Light traveling through this kind of space naturally spreads out more over distance. An open universe is infinite in extent. No loops. No returning paths. It goes on without end and has no boundaries. On top of that, its geometry tends to favor a future where expansion never fully stops. It might slow down, but it doesn't reverse. Galaxies keep drifting away from one another. The universe grows thinner, colder, quieter, over unimaginable stretches of time. In that distant future, stars die out, matter spreads thin, and the universe approaches a state sometimes called heat death, not because it's hot, but because there's no useful energy left to do anything interesting. Just a vast, fading stillness. These three pictures, flat, closed, open, aren't just doodles on a blackboard. They are real solutions to Einstein's equations of general relativity. They describe how space behaves under the influence of mass and energy, how time is warped, how gravity curves the stage, and the shape we end up with isn't chosen like a menu option. It falls out of one crucial ingredient, density. Not just how much ordinary matter there is, stars, gas, dust, but the total energy density of everything in the universe. Dark matter, dark energy. Radiation. All the forms mass and energy can take, added together and compared to a special value called the critical density. If the actual density is exactly equal to that critical value, the universe is flat. If the density is higher, space curves inward, a closed universe. If the density is lower, space curves outward, an open universe. So how do we find out which version we live in? We measure. Patiently, over and over, we study the cosmic microwave background, that faint ancient glow from when the universe was young. We look at how tiny fluctuations in its brightness are arranged across the sky. Those patterns are sensitive to the geometry of space. They carry the imprint of how the universe bends on the largest scales. We also map how galaxies are spread out, how they cluster. We watch distant supernovas grow dimmer with distance, and use them as markers of expansion. We measure how gravity bends light from objects behind massive structures, an effect called gravitational lensing. All of those clues point toward the same answer so far. The universe appears to be flat, or so close to flat that any curvature is smaller than our current ability to detect. If there is a bend, it's very subtle. Our instruments see a cosmos that, on the biggest scales we can probe, behaves like flat space. That doesn't mean the universe is perfectly flat. It doesn't guarantee that it's infinite. It doesn't lock in its fate forever. It just means that right now, from our limited vantage point, it looks flat enough. And flat doesn't mean simple. A flat universe can still be busy. It can still expand and even accelerate. It can still weave giant webs of galaxies, long filaments and empty voids. It can still give birth to stars, to black holes, to planets, and light and everything we see. Flatness just describes the backdrop, the geometry of the stage. What plays out on top of it depends on the actors, on what the universe is filled with, and those contents are strange. Most of the energy in the universe isn't in the form of stars or gas. It's in something we call dark energy, a mysterious ingredient that seems to fill space itself. We don't know exactly what dark energy is, but we know what it does. It makes the expansion of the universe speed up over time. That acceleration doesn't change whether the space is flat or not. But it changes the story of what happens next. In a flat universe with enough dark energy, expansion doesn't slow and stop. It goes on forever, faster and faster, on large scales. Galaxies drift away from one another until many of them slip beyond what we can ever see. The night sky grows emptier. Stars burn out. Black holes evaporate on timescales, so long they barely feel like numbers at all. What remains is a universe that keeps expanding, quieter and colder, with less and less happening. So when someone asks, is the universe flat, open, or closed? The best answer we have right now is, as far as we can tell, it's flat. But that answer comes with little asterisks. There are uncertainties, measurement errors, assumptions about dark energy and how the early universe behaved. We're still refining the picture. The question itself is just one piece of a bigger search. What is the true geometry of space? What is the long-term fate of expansion? What is the actual shape of everything? That there is one clear thread that runs through all three models: flat, open, and closed. None of them require an edge. Flat space doesn't just stop. Open space doesn't stop. Closed space loops back on itself, without needing a wall. The idea that space must end somewhere, with a final border you could stand next to, simply doesn't appear in these equations. The universe in these models isn't an object sitting inside a bigger box. It is the box. Whether it's flat, open, or closed, there is no outer side. No direction you can travel that takes you to outside of space. Only more space, curved or not, and the rules that shape it. So instead of asking, where does space end? It might be more helpful to ask, what kind of space are we inside? What are its rules? How does it bend? How does it connect back to itself? Because once we know more about that geometry, we understand a little more about what it really means to move through the universe, to look out into it, and to live our tiny lives within it. Now that we've let space bend a little in our minds, inward like a sphere or outward like a saddle, there's a natural question hanging in the air. If a space can be finite and still have no edge, how does that actually work? How can something be limited and yet never give you a hard stopping point? At first, that sounds like a trick. We're so used to borders. Rooms have walls. Screens have frames. Pages have margins. Even the ocean, which feels endless when you stare at it, is really held by the roundness of the earth beneath it. We like shapes that end. Our brains feel safer when they can trace a boundary and say, here it stops. But not everything has to behave that way. In mathematics, there are spaces that are both finite and unbounded. They don't go on forever, but they also don't have a place where they stop. You can keep moving through them without ever falling off or running into a wall, and yet the total amount of space inside is still limited. That's what boundless but finite means. It sounds like a riddle, but it's a very real possibility. It might even describe the shape of our actual universe. To ease into that idea, start small. Imagine a perfect circle drawn on a piece of paper. Not the inside, just the line itself. That line has a length. You can measure its circumference. It's finite, but it doesn't have an endpoint. You can pick a point, stand there, start walking along the circle, and you'll never hit an edge. You'll just keep going and eventually come back to where you started without ever stopping or turning around. No boundary, just a loop. That's a one-dimensional example. Now step up a dimension. Picture the surface of a sphere, like the Earth. Not the solid ball underneath, just the outer shell. That surface is two-dimensional. You can move north-south, east-west, but you're always stuck to the skin of the planet. That surface has a finite area. There's only so much surface Earth to go around. But it doesn't have an edge. You can fly around the globe as many times as you like. You'll never find a cliff where the world ends and you fall into something else. The path just keeps wrapping. Now, take one more step that our intuition doesn't really like. Imagine a three-dimensional version of that idea. Not a sphere sitting in space, but a whole three-dimensional space that curves back on itself in every direction. The three-dimensional analog of the sphere's surface, it has a limited total volume. There's only so much space, but it has no outer wall. No last galaxy marking the rim. No outer air, it sits inside. You can move in any direction, keep going forever. And eventually, in principle, you'd return to where you started. Not because you looped around a ball in front of you, but because the space itself is a loop. That's what a finite, unbounded universe could be like, complete in itself, self-contained. No outside, no beyond, everything included in the geometry. We can't really picture that in full. Our brains weren't built to visualize higher dimensional shapes folding back into themselves. We can only borrow analogies, circles, globes, surfaces, donuts. We can sketch slices, draw diagrams, make computer simulations. The real thing lives in equations and models, not in a simple picture book in our heads. But in physics, that doesn't make it any less real. What makes a shape real isn't how easily we can imagine it, it's whether it explains what we see. How does light bend? How do galaxies spread out? How do the faint patterns in the cosmic background glow, arrange themselves in the sky? Those observations whisper clues about the underlying structure. The idea of a finite but unbounded universe is one of the possibilities that fits the clues. We don't see a wall, we don't see a sharp border where space stops. We also don't see obvious repeated patterns that would suggest a very small loop, where light is already wrapped around and shown us the same structures twice. So, the math leaves open an interesting option. Space might gently curve back on itself on a scale so enormous that the loop is bigger than the part we can currently observe. The universe could be finite overall, but so large that from our viewpoint, it behaves almost exactly like an infinite one. And that's the subtle part. A boundless but finite universe feels a lot like an infinite one from the inside. You can travel in a straight line forever. You never run out of room. You never slam into a boundary. From your point of view, space just keeps going. But in a strict sense, it doesn't. It closes. It reconnects. If you could follow a straight path long enough, you'd eventually return home, even if the journey took longer than the entire current age of the universe. This is where the balloon comes back in. The balloon's surface is boundless and finite. So is the globe. There's another nice example. A torus, a donut shape. You can think of it as a flat rectangle where opposite sides are glued together. Step off the right edge, you appear on the left. Walk off the top, you come back in at the bottom. No edge, just connection. Now imagine that kind of stitched connection happening in 3 dimensions. Walk straight through space, and, eventually, you come back from the other side, not because you turned, but because the universe quietly wraps. That idea is more than curvature. It's topology, the way space is sewn together, not just how it bends, but how it connects back to itself. And here's a key point, that stitching doesn't need an outside. It doesn't have to be folded inside a higher room. It doesn't have to sit in some larger container. The connections themselves are the space. This has real consequences for how we think about travel and light and even the history of the universe. In a boundless but finite universe, a beam of light could, in principle, go all the way around and return from behind. If the universe were small enough, you might look into the sky and see a galaxy in 2 directions, once from the front and once from the back, After its light has completed a long loop, you could, in theory, see multiple images of the same object, separated by enormous stretches of time. We've looked for hints of that, repeated patterns, mirrored structures, matching circles in the background radiation. So far, we haven't found any convincing signs. That doesn't kill the idea. It just tells us that if the universe does loop, the loop is probably larger than the part we can currently see. The cosmic round trip would be longer than the universe's current lifetime. Light simply hasn't had enough time to circle all the way. So the loop could be real, but unreachable. That's the gap between what might be true and what we can actually observe. Between what the equations allow and what any telescope can test. Even so, just knowing that this is possible shifts how we think about edges. You can't judge the existence of a boundary by size alone. It depends on structure, on how space bends and how it links to itself. You can build a video game world that's infinite in feel by constantly generating new terrain as the player moves. From inside, you never find a wall. There's always more. You can also build one that loops like a torus. Walk long enough in one direction, and you end up back at the starting point. Again, from inside, you also never find a wall. Both worlds feel boundless to the player. But one is genuinely endless. The other is finite and wrapped. From your character's point of view, they're almost indistinguishable. No edge in either. Different under the hood. The same logic circles back to our own universe. When we ask what it's expanding into, whether it has an edge, whether it's infinite, all those questions really reduce to a quieter one. How does space behave when you move through it? Does it loop? Does it curve? Does it connect back on itself? Or stretch on without closing? None of those possibilities require a wall. You don't need an edge to be finite. You don't need an edge to be infinite. You just need a geometry, a structure, a way for space to be stitched together. The mystery isn't so much where space stops, it's how space works. If space really did have an edge, where would you put it? You can feel your brain reaching for something familiar. You might imagine it like a border on a map, or the last fence at the edge of a field, or the place where the ocean just stops. You could phrase it as a distance. How far do you have to go to reach the end of the universe? You imagine flying in a straight line, faster than any rocket, passing galaxies and clusters and darkness, and finally arriving at what, exactly? A wall? A shimmering barrier? A drop into nothing? Those are the pictures our everyday world trains us to use. Everything we know seems to come in containers, and containers have ends. You walk to the edge of a forest and find a road. You sail to the edge of a lake and reach shore. You leave the edge of a city, and suddenly there are fields and open land. In each case, you move from something into something else. The forest ends, but the road continues. The lake ends, but the land begins. There is always another place for you to enter. So when we think about space, it's tempting to imagine the same pattern. The universe is a big thing, so surely it must be surrounded by something else, and somewhere there must be a line between the two. But as far as we know, space isn't inside anything. It's not laid on top of a larger platform. It doesn't sit in a bigger room. Space is the collection of all wheres, all directions, all positions. Every over there that can exist. If there were an edge, it wouldn't be like the rim of a cup or the last tree before the desert. It wouldn't be a spot you could walk up to, look over, and take a photo of. It wouldn't have coordinates, because coordinates themselves live inside space. Still, we can play with the idea. Imagine we take the fastest thing we know, a photon, a particle of light. We launch it in a straight line with nothing to get in its way. No dust, no planets, no stars, no mirrors, just pure, empty space. The photon moves at the speed of light. It doesn't get tired. It doesn't slow down. It doesn't decide to stop and think. It just goes. From our point of view, we can picture that photon crossing the universe. But there's a twist. While it's moving, space itself is stretching. So as the photon races towards some distant region, That region isn't just sitting there, waiting. The space between here and there is expanding. The distance itself is growing, even while the photon tries to close it. In some directions, the photon might still win. For a while, it can reach galaxies that aren't receding too quickly. But beyond a certain distance, the expansion of space becomes too strong. Those far-off regions are being carried away faster than light can ever make up the gap. Not because they're breaking the cosmic speed limit, but because the metric, the ruler that measures distance, is stretching under their feet. That leads to something quietly dramatic. There are parts of the universe that are forever unreachable, not just for us, with our clumsy rockets, that as clumsy rockets. For anything, no signal starting here, not even a photon leaving now and traveling forever, will ever get there. That invisible limit is called the cosmic event horizon. It's a kind of edge of influence, not a wall, not a shell, but a boundary in what's possible. Inside that horizon, events can, in principle, still affect us someday. Beyond it, events are permanently disconnected. They happen, but they will never show up in our sky. This horizon isn't a physical object. You couldn't paint it or bump into it. It's defined by the expansion of space and the history of time. How fast the universe is growing, how long it's been doing that, and what that means for the paths that light can take. Right now, that no-return distance is estimated to be on the order of tens of billions of light-years away from us. Past that, anything we do now will never matter there. Not in a million years, not in a trillion, not ever. But that still isn't an edge of space, it's an edge of interaction. Beyond that horizon, space continues, galaxies exist, stars are born and die. Light travels. Gravity pulls. Just not in any way that can ever touch us now. If you could somehow ride along with that photon, it wouldn't smash into a barrier at that horizon. It wouldn't ricochet back. It would just keep going, always entering new regions, always moving into more space, unless of course the universe loops back on itself, in which case the photon might eventually return from another direction, but so far, we don't see strong evidence for that. Now pause for a moment and think about what this means for the idea of an edge. If you could ask that photon, where is the edge of the universe? It wouldn't have an answer. At light speed, some very strange things happen. Time, from the photon's point of view, doesn't pass. Distances don't stretch. Its entire journey is not a long line, but more like a single, timeless event. No before, no after, no path, just a connection. For us, moving slower, the story stretches out. We see the path like a long, glowing thread across expanding space. But that thread never runs into a sign that says end of universe ahead, please turn around. If we zoom out, not in distance, but in scale of thinking, something else becomes clear. Even if an edge existed, it wouldn't behave like a feature on a map. There'd be no marker, no change in color, no line that grows bigger as you approach. It wouldn't bounce light back to your eyes because there'd be nothing on the other side to reflect from. In fact, if space really ended, the word edge might not be quite right anymore. Edges normally separate two things: inside and outside, object and not object. But if there is no outside, no other side at all, then what exactly is the edge dividing? To say end of space implies that beyond it is, what? Not empty vacuum. Because vacuum is still a kind of space. Not darkness. Because darkness is just a region where light hasn't arrived. Beyond an edge of space would be something like no space at all, no distance, no direction, no over there. Just the absence of dimension. Our language doesn't handle that very well. We want to call it nothing, but we imagine nothing as a kind of eerie black room. A void you could float in, a blank, silent place. But true nothing. No space, no time, no matter, no structure. Isn't a place, It doesn't have a location. It doesn't even have a where for you to put it in. You can't say it's dark, because darkness needs somewhere to be. You can't say it's empty, because emptiness is still a property of space. So asking where is the edge becomes a strange kind of question. It's like asking what's north of the North Pole. It seems reasonable at first, but the question quietly asks for something that doesn't exist. Some people picture a sort of membrane at the edge of space, a border between space and not space. But what holds that membrane up? What is it made of? If it's a physical thing, then it must exist in space, and then it's just another object, not an edge. Others imagine the universe ending like a video game world, where the map simply stops, a cliff into nothing. You walk too far, and suddenly there's just absence. But in real physics, that's hard to justify. What would keep particles from moving past that invisible line? What stops light? Why would the rules suddenly halt? We don't see anything in our current understanding of the laws of nature that demands a hard stop, like that. Space doesn't seem to want to just terminate at a random, unmarked boundary. So, step by step, the question shifts. It moves from, where is the edge, to does edge even apply here? And from there to something more practical and grounded. What does space do? How does it behave? What can signals reach? What can we observe? What can we test? That leads us to a different kind of edge, one we can actually define, the edge of the observable universe. This isn't an edge of existence. It's an edge of information. Think of it this way. Light has been traveling since the universe became transparent, shortly after the Big Bang. Space has been expanding the whole time. There's only so far that light could have gotten to us in all those billions of years, given that expansion. That maximum distance forms a kind of bubble around us, roughly 46 billion light-years in every direction. That's the radius of our observable universe. Not how far we can travel, how far light has traveled to us. Beyond that sphere, more space almost certainly exists. More galaxies, more matter, more structure. But we can't see it. Not because it's behind a curtain, but because its light simply hasn't arrived yet. And some of it never will. This observable limit is another sort of edge, not a hard barrier. A soft one, made of time and the speed of light, a horizon of knowing. We didn't build that border. We just live inside it, like people standing in a circle of candlelight in a dark field. The darkness beyond doesn't mean nothing is there. It only means the light hasn't reached us yet, and that leads to a deeper question. If we can't reach the edge, and we can't see past it, how can we even say space continues? Are we just assuming? Are we using patterns and hoping they still hold? In a way, yes. We look at what we can see. We see that space looks smooth and similar in all directions, on large scales. We see that there's nothing special or strange happening. Right at our observational boundary, no sudden drop in galaxy numbers, no sharp edge in the cosmic glow. So the simplest interpretation, the one with the fewest special tricks, is that space continues beyond our view in roughly the same way. We can't prove that. We can't test regions beyond our horizon directly. But the models that fit our data don't suddenly stop the universe at 46 billion light-years. They just let it go on. So, for now, it's enough to say this. If space has an edge, a true end, it doesn't act like the edges we know. It's not a place you can reach. It's not a wall you can knock on. It's not a line you can draw on a chart. It's something more abstract, tied into the very meaning of space and nothing and where. Or maybe it's simply not there at all, and between those possibilities, we float. Somewhere inside a bubble of light, surrounded by a universe that may go on much farther than we can ever see, with edges that are less like walls and more like the quiet limits of what's reachable, what's knowable, and what our questions are built to imagine. Space grows. Not like a balloon popping in your hands or a wave crashing against the shore. Not like a car racing across a road. There's nothing sudden or dramatic about it when you zoom in to human scales. It's slow, smooth, and constant, quiet enough that you'll never feel it happening, even though it never actually stops. When we say space is expanding, we are not talking about things moving through space the way cars move down a highway. We're talking about space itself becoming more spacious. The grid underneath everything is stretching. The scale changes, even if the objects sitting on that scale don't seem to go anywhere locally. The stretching began around 13.8 billion years ago, not from a single point out there in some larger void, but from a state where the universe was hot, dense, and as far as we can tell, pretty much the same everywhere. There was no special spot you could point to and say, it all started here. The expansion happened everywhere at once. Every region of space began to drift apart from every other region, and that drift has never fully stopped. It's easy to assume that expansion is like throwing a ball into the air. It goes up, slows down, and eventually falls back, or like pulling a rubber band that snaps back into place. Something starts fast, loses energy, and relaxes, but space doesn't behave that way on its own. Its expansion isn't driven by a single burst of momentum that has to run out. It's governed by the deep rules that connect matter, energy, and the shape of space-time. And the strange part is, over time, the expansion hasn't slowed down. It's sped up. That realization arrived in the late 90s when astronomers were studying distant exploding stars, supernovae, and using them as cosmic mile markers. Those stars looked dimmer than expected, which meant they were farther away than they should have been based on the earlier expansion rate. The only way to make the numbers work was to accept something unsettling. The universe had started expanding faster with time, not slower. Space was stretching more quickly now than it did in the past. To explain that, scientists introduced the idea of dark energy, not a fog filling the cosmos, not a wind pushing galaxies apart, but more like a built-in property of empty space itself, a quiet pressure that makes space expand more and more over time. It isn't that galaxies are being shoved away by some force acting between them, like tiny hands. It's that the space in between them is stretching. And because dark energy seems to be tied to space itself, the more space there is, the more dark energy there is, and the more stretching you get. More space means more dark energy. More dark energy means more expansion. More expansion means more space again. It's a feedback loop, a self-reinforcing drift. In that kind of universe, expansion doesn't settle down. It doesn't coast to a stop. The distances between galaxies grow faster and faster, and over long enough timescales, most of those galaxies will move so far away that their light can no longer reach us at all. Not because they disappear, but because the stretching outpaces their ability to stay in touch. They slip beyond our cosmic event horizon, that invisible limit past which no new signal can ever arrive. From us, they vanish, not in a puff of smoke, but in silence. Just gone from our sky. In a universe like this, the word edge becomes slippery, because even if you pick a galaxy you can see right now, point toward it, and imagine flying at the speed of light trying to reach it, the universe works against you. As you go, the space between you and that galaxy is still stretching. The distance you're trying to cross keeps growing. At some point, that growing distance starts to widen faster than light itself can bridge it. You're not breaking any rule by trying. It's just that the ruler you're using, the one that measures the space between you and your goal, is being stretched faster than you can move along it. You can't outrun the changing scale. The result is subtle, but brutal. Some galaxies we can see today are already lost to our future. The light they're sending out now will never reach us. The photons currently leaving them are doomed to fall behind the expansion. We'll only ever see them as they were in the past, never as they are later. Over immense spans of time, more and more galaxies will cross that horizon. The universe we can see will shrink, not in size, but in content. The lights will wink out one by one, not because the galaxies stop existing, but because they're carried too far away for their messages to get through. Eventually, only the galaxies bound to us by gravity, our little local group, will remain visible. Everything else will be swept beyond reach by expansion, into a darkness no telescope can ever pierce. Imagine an astronomer billions of years from now, standing under that future sky. They might see only a handful of nearby galaxies, and nothing beyond. No wider web, no grand cosmic tapestry. Even the faint afterglow of the Big Bang could fade beyond detection. To them, the universe might look small and lonely, not because it is, but because expansion has erased the evidence. That isn't a science fiction twist. It's what the equations say should happen if the acceleration continues the way it appears to now. And this has another consequence. If the universe does have some kind of edge, some ultimate outer limit to space itself, it's not just far away, it's unreachable in principle. The route to it would keep growing faster than anything could ever travel. You could devote the entire lifetime of the cosmos to rushing toward that hypothetical boundary, and you'd still never arrive. The path lengthens faster than you can progress along it. The edge, if it exists, lies beyond not just our technology, but our causal reach. Beyond what can ever be known. That's why cosmologists don't really think in terms of going to the edge. In a universe with accelerating expansion, the edge isn't something you approach. It's something that sits forever outside the part of reality that can interact. So when people picture the universe expanding, it's natural to imagine a big explosion into emptiness, matter flying outward into a waiting void. But the real story is stranger and, in a way, calmer. Space expands because, on large scales, that's simply what the current rules cause it to do. Because the energy of the vacuum itself nudges it to grow. Because there's no opposing force big enough to pull everything back together again. This expansion doesn't feel like a temporary phase. It doesn't look like a process that's winding down. As far as we can tell, right now, it is the state of the universe. Could that change? Maybe. We still don't know exactly what dark energy is. It could vary with time. It could fade. It could even reverse its effect someday. But based on what we're seeing now, that's not the story the universe is telling. Right now, space just keeps stretching. It carries galaxies away from each other. It carries light away from us. It pushes the observable edge of our universe outward, while, paradoxically, letting more and more of the real universe slip beyond our sight. Some corners of space are already gone to us forever. Not because we ignored them, not because we chose not to look, but because by the time we started looking, the universe had already pulled them too far away. So when we ask, does the universe have an edge, we quietly have to add another question underneath. Even if it did, would we ever be able to know? Would there be any sign, any signal, any clue that could reach us before the expansion carried that information beyond our horizon? Or would the edge, if it exists, always remain just beyond the last thing we can touch, forever outside the circle of what can be seen, measured, or confirmed? That uncertainty is part of the mystery. Not just where the universe ends, but whether the very idea of ending still makes sense in a reality that stretches faster than anything inside it can run. The bit of the universe we can see is like a small lit circle in a much larger darkness, not because the rest is empty, but because light has only had so long to travel. What we call the observable universe is just that lit circle. It's the region of space from which light has had time to reach us since everything began to expand and cool. If you imagine us sitting in the middle, it forms a kind of sphere around us, stretching tens of billions of light years in every direction. We sit at the center of that sphere, but not because we're important. It's just how light works. You always see the part of the universe that has had time to send you a signal. If you were on a galaxy billions of light years away, you would also see yourself at the center of a similar bubble. Every observer, everywhere, draws their own circle of visibility. Out at the edge of our bubble, the light is stretched and faint. It comes from very early times, when the universe was young and hot. That shimmering limit isn't a physical shell. There's no membrane, no wall, no change in the rules. It's just the distance that light has managed to cross, given the age of the universe, and the way space has been expanding, and beyond that, as far as anything we know can tell, space simply continues. There's no sign of a sudden cutoff where the last galaxy hangs alone like a final ornament on a branch. The patterns we see inside our bubble, the way galaxies cluster, the faint mottling of the cosmic background glow, the overall flatness and smoothness, all suggest that the same kind of structure goes on past the horizon. If you could somehow step outside our bubble and look back, you probably wouldn't see a border. You'd see more universe, more galaxies, more space, more time unfolding. We assume that's true because there's nothing special about the edge we see. No equation says stop here. No observation says the rules change at this radius. Stopping the universe right at the point our light happens to fail would be oddly arbitrary. Like declaring the ocean ends exactly where your flashlight beam fades, just because you can't see further. But assumption is not proof. We really don't know what lies beyond our observable patch. We can't measure it. We can't take a picture. All of our models, even the ones that say the universe might be infinite, are built from what we can see. And what we can see is just a small fraction of whatever is really there. If the universe is truly infinite, then our observable bubble is just a tiny spot in a never-ending expanse. A pinprick in an ocean of galaxies, not small in itself, but utterly dwarfed by the total. If instead, the universe is finite but large, if it loops or folds or wraps around in some higher dimensional way, then our bubble is still only a piece of that whole. In that case, we're looking at a patch of a cosmic surface, not the full shape. We're still missing the rest. We're still taking guesses. So the question isn't only what lies beyond what we can see. It's also how much more is there beyond what we can see? And an even sharper question, can we ever know anything about it at all? In practice, probably not. No signal can outrun light. No telescope can peer into places whose light has no path to reach us. There are no cosmic shortcuts we know of, no tunnels through space-time to jump the queue. Regions beyond our observable horizon are not just far away, they are causally disconnected from us. They live outside our light cone, outside the web of events that can ever touch us or be touched in return. That sounds lonely, but it's not unique to us. Every point in the universe lives at the center of its own observable sphere. Some of those spheres overlap, others don't. Two galaxies separated by enough distance may never see each other at all. Each one experiences its own private version of all that exists, shaped entirely by what light has had time to tell it. You don't actually need an edge to be confined. All you need is limited time and a finite speed for information. Now imagine the parts we'll never hear from. There are galaxies already too far away, moving away too quickly, with the expansion of space, whose light will never reach us. We will never see their stars, never detect a single photon that left them after a certain point. If new galaxies form out there tomorrow, if new suns ignite, if life arises and builds radios and sends signals into their sky, none of that will ever reach us. They're not hidden, they're unreachable. We're not missing them because our telescopes are weak or because we're not trying hard enough. We're missing them because we live in a universe where distance and expansion together create permanent separation. That isolation isn't a malfunction. It's part of the design of space-time as we understand it. Even so, we're not completely blind about what lies beyond. We can't see it directly, but we can use what we do see as a clue. We measure the cosmic microwave background, that afterglow left from when the universe was very young. We map the way galaxies cluster and form filaments. We watch how structures grow over time under gravity and expansion. All of that lets us infer what the universe is probably like, just beyond our view. And everything so far points toward a simple picture. On very large scales, the universe looks roughly the same, everywhere. Not identical in detail, but smooth, uniform, following the same basic rules. That's the easiest, most natural reading of the data, and it's the foundation of many cosmological models. But nature never signed a contract saying it has to stay that simple. Just beyond the horizon, reality could change. Space could curve sharply. The density of matter could drop or spike. The laws of physics could twist into slightly different forms. The universe could branch or fracture or even stop in some way we haven't imagined. We wouldn't know. We couldn't know, at least not directly. That's part of what makes this so strange. We're used to thinking that anything real can be observed if we just build a good enough instrument and wait long enough. But the observable universe reminds us there are hard limits. Not only of patience or technology, but of what seeing can ever mean. Still, the questions don't go away. We start to wonder, could there be other vast regions of space beyond our own, separated not just by distance, but by history? This is where ideas like the multiverse step in, not as fantasy, but as a possible consequence of certain theories about the early universe. Some versions of cosmic inflation, that early burst of rapid expansion, suggest that what we call our universe might just be one bubble in a larger foam. Inflation might not have ended everywhere at once. It could have stopped in one region, forming a universe like ours, while continuing elsewhere, spawning other regions with their own expanding spaces, their own properties, maybe even their own versions of physics. Each bubble would be a universe from the inside. Together, they'd form a multiverse. If that picture is right, our observable universe is a tiny part of one bubble among many. And those other bubbles, if they exist at all, are separated from us by regions of space that expand too fast to cross. No light, no signal, no gravitational tug can ever make the journey between them. We can speculate. We can build mathematical models. We can see whether those models also explain the things we can observe, like the patterns in the cosmic background glow, but we can't stick our head out of our own bubble and check. So what lies beyond our observable universe? Possibly more of exactly what we see, possibly something very different. Possibly other bubbles of reality altogether. Possibly, in some directions, nothing at all. What we know for sure is quieter and simpler. Space doesn't end where our vision stops. The edge of the observable universe is not the edge of the universe itself. It's just as far as light has had time to talk to us. Beyond that, the cosmos continues. In what form, we can't yet say. And in that continuing, it leaves us with a gentle reminder. No matter how far we look, no matter how many galaxies we count, we are always surrounded by more distance, more possibilities, more unanswered questions. Not just in space, but in mystery. Think for a moment about how many things in your everyday life have a clear middle. A room has a center where you might put a table. A circle has a neat little point in the middle you can mark with a pen. A city has a downtown, a heart where the streets seem to converge. Even a tree has a trunk that everything else seems to grow out from. So when someone says, "The universe began with the Big Bang," your mind almost automatically builds a picture. You imagine a point in empty space, then a huge explosion, and galaxies flinging outward like glowing sparks from a firework. And if there was an explosion, there must be a central spot where it happened, right? A place where it all began. That picture feels natural. It's also deeply misleading. The real Big Bang, as far as we understand it, wasn't an explosion in space. It was an expansion of space. Not a blast that happened somewhere inside a room, but the room itself growing from an incredibly small, incredibly hot, incredibly dense state. Space wasn't sitting there waiting, like an empty box. Space itself came into being and began to stretch. The fabric that would later hold galaxies and stars, and you and everything else, wasn't filled up. It was created and then enlarged. That's why talking about a center of the Big Bang doesn't really make sense. There was no special point where it started, no cosmic downtown where all the galaxies came from. Every point in space was involved from the very beginning. Everywhere you could stand now was once part of that hot, dense, early universe. As expansion began, every region of space started moving away from every other region. Not because something pushed the matter outward from a center, but because the space between things grew. Imagine dots drawn on a balloon. When you inflate the balloon, every dot moves away from every other dot. You can pick any dot you like and say, "Look, everything is moving away from this one." But there's no dot that's truly special. The center of the expansion isn't on the surface at all. Our universe is like that, but without the outside air and without the rubber skin. The expansion is happening within space, not into something else. There's no central dot, no privileged place where the Big Bang happened. It happened everywhere at once. And this leads to one of the strangest truths in cosmology. No matter where you are in the universe, if you look around, it seems like everything is moving away from you. From Earth, we see distant galaxies receding in all directions. If you were living in one of those galaxies instead, you'd see the same thing. Galaxies rushing away from you in all directions. It's not that we're at the center of everything. It's that expansion looks the same from every vantage point. Every point in space is, in a sense, the center of its own observable universe. Not because everything revolves around it, but because every point is surrounded by light arriving from all sides. Light that has taken billions of years to travel. Light that defines the sphere of what you can see from where you are. We build our maps centered on Earth because that's where our telescopes sit. Our instruments look outward. Our data falls inward. So on a chart, we end up in the middle almost by default. But those maps are just perspectives. They don't show where we are in some grand layout. They just show where we are relative to what we can see. If you built the same map from a distant galaxy, it would look very much the same. Different labels, different local neighbors, but the same basic shape. You in the center, galaxies all around, space expanding in every direction. The center, in this sense, isn't a physical location, it's a point of view. That's not easy to really feel in your bones, because our everyday lives are built on fixed directions, up and down, left and right, near and far. You throw a ball from one side of a room to the other. It follows a clear path. You watch a clock tick forward. Time seems to flow in one direction, from before to after. On cosmic scales, those simple ideas start to wobble a little. Direction becomes relative. There is no universal up. Movement becomes tied to the expansion of space. Things don't just move through a fixed backdrop. The backdrop itself changes. Time becomes more like a coordinate on a map than a steady river you float along. You can label events with when, just like you label locations with where, and both of those depend on how you move and where you stand. So when we ask, where did the Big Bang happen? Or where is the center of the universe? We're sneaking in assumptions from everyday life that don't apply. The Big Bang didn't happen at a location, it happened as a moment. A moment when the universe was in a particular state and started to expand and cool and form structure. It's not a dot you can fly toward. It's a time you can look back at in the light that's still reaching us. And because space itself has no known edge, the idea of a central point gets blurry. You can't pick a middle without a boundary to measure from. A loop has no first point. The surface of a sphere has no special spot that counts as the true center of the surface. On a globe, the North Pole is special only because we choose it. Geographically, every point on that surface is just as much on the Earth as every other. There's no ring around the ball that says, this is the origin. The universe seems to be like that in 3 dimensions. Every point is just as much in the universe as any other. There is no signpost that says, this is where it all started. This is the true middle. Even the idea of before the Big Bang might not make sense in the way we want it to. Time, as far as we can tell, starts with that event. Not in the sense that something pressed a magical start button, but in the sense that the equations we use to describe the universe only work from that moment onward. There wasn't a long stretch of empty time ticking away in silence, waiting patiently for the Big Bang to happen. Time itself is part of the universe's structure. No universe, no clock, no before. There are models that try to peer further. Some imagine earlier phases of contraction and expansion, cycles and bounces. Others picture collisions between higher dimensional brains, where our universe is one sheet colliding with another. Some propose that the Big Bang was just one event in a much larger, possibly eternal reality. But even in those ideas, one principle keeps showing up. There's no absolute center of space. The expansion isn't rising out of a single location into a larger room. It's happening within the system itself, everywhere. The universe on large scales looks homogeneous, roughly the same everywhere, and isotropic, roughly the same in every direction. That's not just guesswork. We see it in the cosmic microwave background, the faint glow left from the early universe. Wherever we look, that glow is almost the same temperature, with only tiny ripples. No big hot spot in one direction, no obvious sign of a cosmic middle. Those tiny ripples are important, though. They're the seeds from which galaxies eventually formed. But on the whole, the pattern is smooth, even, spread across the sky in a way that suggests there's no preferred spot. Inflation theory tries to explain that smoothness. It proposes that in the first fraction of a second, the universe expanded faster than light can travel, ironing out irregularities and stretching space so much that on large scales, everything looks uniform. That early smoothing is helpful, but it also hides information. If everything looks roughly the same from everywhere, how do you figure out what's beyond what you can see? If there's no center and no edge, how do you describe the shape of the whole? Those questions shift us from thinking about where to thinking about how. How does space connect? How do distances behave? How do straight paths curve or fail to curve? Does space loop around, or does it continue without closing? Those are questions of geometry and topology, of structure and connection. They don't care where you stand, they care how the universe behaves. To answer whether space can fold, whether it can stretch infinitely, whether it can end in some strange way, without having a simple wall, we have to let go of the craving for a central spot. We have to stop trying to label one place as the origin, the cosmic trunk, the one true middle. In the biggest picture we have so far, there isn't one. There's only space-time and the rules it follows. There's only the way it curves, the way it stretches, the way it evolves. The comforting part is, you don't need a center to feel grounded. You don't need the universe to pivot around you to matter. Every measurement you make still counts. Every galaxy you see still moves the way the equations say it should. Every atom in your body still dances to the same physical laws that govern distant stars. You are not at the middle of everything, but you are within everything, inside the same structure, subject to the same rules, part of the same unfolding. The center isn't where you are, it's just how you look. And when you finally let that go, when you stop hunting for the one special point, and instead ask, what is the whole like? Something opens up, the expansion becomes easier to picture. The shape of space feels less like a map and more like a living pattern. The questions themselves start to change, not where did the universe begin, but what caused it to begin in this way. Not where does it end, but does ending even apply? Not where exactly are we in the grand layout, but what kind of thing is the grand layout at all, and how does it behave in that shift? The universe stops being a place with a center and becomes a structure with a story. And you, wherever you are, however you are lying or sitting right now, are one tiny, thinking part of that story, wondering about the whole from the inside. If there's no middle to stand in and no outer fence to lean on, then what does infinity really feel like? Not as a symbol on a blackboard, not as a fancy math word, but as something you could, in principle, walk through, something you could fall into, not to reach the end, but just to keep going. When you hear infinity, it might sound far away from real life, like it belongs to chalk dust and equations. But in cosmology, it's not just decoration. Infinity shows up as a serious option for how space might actually be. The idea is simple to say and hard to picture. You stand somewhere, anywhere. You look around. In every direction, space continues. Not for a long time and then stops, not until some outer skin. Just on. No wall, no loop that brings you back, no curved edge to turn you around. Only more space. That's one possible way the universe could be. Not the only one. We've talked about spaces that curl and spaces that wrap back on themselves. But right now, the measurements we have, from the faint afterglow of the early universe, from how galaxies clump, from how matter is spread out on huge scales, all say the same quiet thing: space looks flat. Or, if it's curved at all, it's curved so gently that we can't see it. In a flat universe with the right overall structure, space doesn't have to fold back. It can just keep going. No edge, no total amount of space, just more. If that's how things really are, then the bit we can see, our observable universe, is only a small patch in a much larger expanse. Our familiar bubble of galaxies and background light is just where the light has reached us so far. Outside that bubble, space may simply continue in the same way, no sudden change, no border, just more of the same kind of cosmos, stretching beyond anything our telescopes can sample. In a universe like that, the idea of falling into forever becomes less poetic and more literal. Not because you'd actually float through it, but because in principle, you could pick any direction and walk, or fly, or ride a beam of light forward without ever exhausting the path. You'd never find a sign that says, "Last galaxy ahead." You'd never see the sky thinning toward a final star. No matter how far you went, there would always be more ahead. More galaxies, more empty voids, more stretches of nothing, punctuated by something. Your eyes and instruments would still be limited. Light only travels so fast. You only live so long. Expansion tugs distant things away, so you'd never see infinity. But the space itself, the invisible coordinate grid underneath everything, wouldn't run out. And that has a strange consequence. In an infinite universe, the number of galaxies isn't just huge, it's not a lot. It's not even bigger than we can count. It's unbounded. You could keep listing galaxies forever and never finish. Same for stars, same for planets, same for regions where life might be possible. There isn't a total number, only more. Now comes the part that bends the mind a little further. In an infinite space, if the basic ingredients are limited, if there are only so many types of particles, and only so many ways they can arrange themselves in a region the size of, say, a galaxy or a solar system, or even a brain, then patterns eventually have to repeat, not just similar patterns, the same ones. Not next door, not in any region we could ever hope to reach, not in our observable bubble, at all. But somewhere, unimaginably far away, the atoms could line up again, in the same configuration they have here. That would mean a planet, very much like this one, a solar system that moves in familiar rhythms. Maybe even, in some models, someone sitting or lying down, listening to a voice talk about infinity and edges and space. It sounds like science fiction. But it's really just what happens when you combine two ideas: limited ingredients and unlimited room for them to arrange themselves. Given an infinite amount of space, even the rarest arrangement doesn't just happen once. It becomes inevitable, over and over again, scattered across distances so huge they might as well not exist for us. But here's the important catch. None of those repetitions would be reachable. Not in practice. Not even in principle. The distances between those far-flung regions would be so enormous, and the expansion of space so relentless, that no signal could ever cross the gap. Not light, not radio waves, not spaceships, not anything. Those mirror patterns remain part of the model, not part of our world. They live in equations and thought experiments, not in any map we could draw. Still, this kind of infinity changes how we picture space. It stops being a box with walls and becomes more like a direction you can always continue in. Not a thing with sides, but a process with no final step. In that picture, you don't reach infinity. You move within it. Any journey, no matter how long, is just a tiny segment of a path that never ends. Any place you stop is still surrounded by more. Gravity and matter don't disappear, of course. You wouldn't drift peacefully forever in a perfectly empty straight line. You'd encounter galaxies, clusters of galaxies, enormous filaments of matter, dark stretches where almost nothing lives. Paths bend. Light curves. You meet obstacles. You change course. But space itself doesn't present a final barrier. If you could somehow go on, there'd be no last coordinate waiting. In that sense, infinity isn't a location, it's the absence of a limit. It's what it means for there to be no final out there. And once you accept that possibility, lots of other ideas shift a little. In an infinite universe, asking for the total amount of energy becomes tricky. There is no total. You can talk about density here, about average behavior in this region or that region, but you can't sum it all. The sum doesn't converge. It just keeps growing as you include more and more of space. You also can't draw a map that covers everything. You can only chart a patch. No survey can claim to be complete. There's always more beyond the edge of whatever you've measured. More stars, more voids, more unknowns. That doesn't mean the universe is impossible to know. It just means it can never be fully known from the inside. There will always be horizons. Always things beyond reach. Always a larger context that you can't quite capture. And if you follow that thought for a while, something subtle happens. You stop worrying so much about how big the universe is in some final, absolute way. You stop asking where does it end, or how far does it go, because those questions start to feel less helpful. Instead, your attention slides toward the rules. How does space behave? How does matter clump into galaxies and stars and planets? How does expansion change over time? How does gravity curve paths and shape structure? Those become the real questions. Because in an infinite universe, boundaries aren't the main story, the laws are. It's the way space curves, not how far it stretches, that tells you how light travels. It's the way matter gathers, not how much there is in total, that tells you where stars can form. It's the way time unfolds, not how long it lasts, that shapes what's possible inside it. Infinity doesn't erase structure, it just removes the outer fence. And in a universe without a fence, the most important things aren't the edges you can't reach, but the patterns you can see, the paths you can trace, the rules you can uncover, and the quiet realization that wherever you are, however far you look, there is always more beyond what you know. It's one of those questions that sneaks back into your mind, even after you've told yourself you've moved on. If you pick a direction in space and just keep going, never turning, never stopping, will you one day come back to where you started? On the surface, it sounds simple. You imagine walking in a straight line, circling a planet, and eventually ending up right back at your own doorstep. Same path, no turns, a long, perfect loop. But when we ask that question about the whole universe, we're not really talking about the path anymore. We're talking about the shape of space itself. The word for that is topology. Not just, is it curved here? But how is everything connected as a whole? Does space close in on itself? Does it keep going without limit? Is there some grand pattern that repeats behind the scenes, too large for us to notice yet? We already know that, on very large scales, space looks pretty flat. If you draw a triangle, using distant galaxies as the corners, the angles add up the way school geometry says they should. Light travels in what we'd call straight lines, and less gravity bends it. Nothing obvious suggests a big overall bend, but flat doesn't automatically mean infinite. That's the subtle part. You can take a flat sheet of paper and do all sorts of things with it. You can roll it into a cylinder. You can glue opposite edges together to make a loop. You can turn it into a shape where walking off one edge pops you back in on the other side. Think of a video game world where if you walk off the right side of the screen, you appear on the left. Walk off the top, you show up at the bottom. To the character inside the game, the world feels endless. There's no wall, no place where you fall off. But from outside, the map is actually small and neatly wrapped. Now imagine that trick in 3 dimensions. You take space, which is locally flat, and you stitch its edges together in every direction. Left connects to right. Up connects to down. Front connects to back. You end up with a universe that has no center and no outer shell. You can move forever and never meet an edge. But the total volume is still finite. That's one example of a flat but finite universe. Cosmologists call shapes like that three-tori, that you can think of it as a room with no walls because all the walls take you back inside. In a universe like that, light itself could, in principle, make a full circuit. A photon could set off in a straight line and, given enough time, end up back where it started, not because it curved, but because space folded back onto itself. If that really happens, it leaves clues. You might see the same cosmic structures more than once in different directions. The same galaxy cluster repeated, the same patterns in the ancient background glow, showing up in multiple patches of sky, like reflections in a hall of mirrors. Scientists have actually looked for that. They've studied the faint cosmic microwave background, that afterglow from the early universe, searching for repeated circles, matching shapes, patterns that line up in a way that says, you're seeing the same region twice. So far, those echoes haven't shown up. We don't see the clear repetition we'd expect if the universe were a small looping space. But we don't see it isn't the same as it isn't there. It might simply mean the loop is huge. So huge that light hasn't had time, in 13.8 billion years, to go all the way around and come back. Imagine a wheel that turns so slowly it completes one spin in 1 trillion times the age of the universe. From where you stand, it looks still, but it's technically turning. That's the strange thing. The universe could be wrapped and looping and finite, and we might never notice because we live inside too small a patch and we haven't waited long enough for light to finish the circuit. So we're left in a familiar place, a maybe that could be true in reality and yet be forever unreachable in practice. Still, the idea of a looping universe is hard to let go of. It has a kind of elegance to it, and a weirdness. In a closed finite space, you can travel forever in a straight line and never leave home. You never hit an edge. You never arrive at outside. You just take the long way round and eventually come back. But here's a twist. Would you even recognize that you'd returned? The universe is expanding. Galaxies are drifting apart. Stars are born and die. Light stretches and fades. If it takes longer than the age of the universe for a full loop, then by the time you arrive back at your starting coordinates, almost everything will be different. The galaxy you began in might be unrecognizable. The stars rearranged, the map rewritten. You would complete the loop in terms of geometry, but not emotionally. It wouldn't feel like coming home. It would feel like arriving somewhere new that happens to share the same address in a space that's been stretched beyond recognition. Light faces a similar problem. If photons circle a looping universe, their paths cross and intertwine. The same beam of light could, in theory, reach us from multiple directions, after taking different routes. You might see your own galaxy from behind, an ancient snapshot showing it as it looked billions of years ago, while you sit inside the current version. That sounds like a cosmic magic trick, but it's really just geometry playing with time. Again, it's testable in principle. We search for those repeated structures. We haven't seen them clearly yet. Maybe they're not there. Maybe they're too subtle. Maybe the loop is bigger than the part of space we'll ever be able to see. Even if we never find them, the possibility stays on the table. The universe may well be a looping structure that's just too large, too slow, too wide for its own pattern to reveal itself to tiny creatures living on a small planet. If it does loop, though, it changes how we think about the whole picture. A looping universe is finite in total volume. There is only so much space, only so much matter, only so much energy. Not because anything is boxed in by walls, but because of how space is connected. You can talk about total mass, total energy, total entropy in a meaningful way. You can say, this is all there is, not because you've hit an edge, but because the structure closes back on itself. It doesn't make the universe feel smaller. It makes it feel more like a complete system. Not contained by a fence, contained by its own geometry. There's another version of looping too. Instead of a flat, wrapped universe, imagine a positively curved one, not a torus, but the higher dimensional equivalent of a sphere. Like walking on the Earth's surface, only in 3 dimensions instead of 2. Go straight long enough, and you eventually return to your starting point. Again, no edges, finite size, all paths eventually meeting up. In that kind of universe, you also get a different possible fate. A cosmos that expands for a while, then slows, then halts, then turns around, space shrinks. Galaxies move closer. Eventually, everything could collapse back into a dense state. A long unwinding of everything that was stretched out. A big crunch instead of a big chill. Right now, that future doesn't match what we see. Expansion isn't easing up. It's accelerating. Dark energy seems to be driving everything apart faster, not letting gravity pull it back in. So our best models point toward continued growth, not reversal. But the geometry still matters. Whether space loops or doesn't, whether it curves or stays flat, tells us something about how the whole is stitched together. And that leads to one last question, hanging at the edge of this part of the story. Suppose the universe does not loop. Suppose it's flat and goes on forever. No closure, no full circle, no big crunch at the end. If it doesn't fold back, and it doesn't stop, and it stretches without limit in every direction, then what, if anything, surrounds it? Maybe the question feels like it has to have an answer, because it's one of the first deep ones we ever ask. Even children try it out. If the universe is everything, what's outside everything? We grow up surrounded by containers. Rooms inside houses, houses on streets, streets in cities, cities on continents, it's boxes all the way up. Everything we know seems to live inside something else. So when someone says, space is expanding, your brain quietly fills in the missing picture. You imagine a balloon swelling inside a room, or a bubble growing inside a larger pool of water. Space getting bigger inside some even bigger space. But the universe doesn't sit inside a room. It is the room. That balloon picture is helpful in some ways. It shows how a surface can grow and stretch, and how every point can move away from every other point without any one point being the center. But the balloon still has something our universe doesn't. An outside. There's the rubber skin, and then there's the air around it. In real cosmology, that outer air doesn't exist. Not in any direction you could travel. Not in a way you could point to, measure, or ever reach. Space doesn't float inside a bigger container. Space is the container. When it expands, it's not moving into a pre-existing emptiness. It's quietly changing what distance means between the things inside it. If you asked, where is the universe? The honest answer would be strange and short. It's not in a place. It is the collection of all places. There's no address to give, no larger set of coordinates you could write it inside of. Even the question, what is it expanding into, carries a hidden assumption. It assumes there's a surrounding realm waiting there like a bigger box. But expansion, in this context, doesn't need a backdrop. Space doesn't pour into more space. It creates new intervals between things. More separation, more distance, more between. That's where our minds start to stretch a bit, because we don't really have everyday examples for this. Everything we build has front and back, inside and outside, edges and walls. The universe, as we currently understand it, has none of that. You can't step out of it. You can't float around to the other side. You can't look down on it from above like a glowing snow globe on a table. Even if space is finite, even if it wraps or loops, it's not wrapped in anything else. Just like the surface of a sphere doesn't need to live inside a drawn box to be complete. The surface is its own whole. Some theories do play with the idea of more directions than the ones we feel. Extra dimensions. Hidden directions curled up too small or too strange to sense. In some of those models, our universe could be like a sheet, a brain, floating in a higher dimensional space. In that picture, there is something like an outside, but it's not an outside you could ever reach by flying long enough. It wouldn't be space like ours, just bigger. It would follow different rules, different scales, maybe even a different idea of distance altogether. And all of that is, for now, unconfirmed. Interesting, clever, mathematically useful in some ways, but not proven. None of those models has given us a clear prediction we've been able to test and see come true. So the best answer we have, today, is oddly simple and oddly unsatisfying. There is no outside to the universe in the usual sense. No extra room it's sitting in, no larger region that holds it, just more universe, or nothing at all. And nothing here doesn't mean empty darkness. It doesn't mean a black void waiting quietly. Even a void is still space. Real, nothing, would be the absence of space and time entirely. No distance, no direction, no before, no after, no way to move, no way to look, no way to even lay down a coordinate grid. You can't travel to that kind of nothing. You can't stand at its edge. You can't point and say, it's over there. Because over there needs space to exist. And if there's no space, there's no there. That's why saying, there's nothing outside the universe, feels like dodging the question. Our minds want a picture, a background, a frame, but imagination itself needs somewhere to put its images. If you remove all space, all time, all content, there's nothing left to hang a picture on. Not even an empty canvas. Just no canvas at all. It's not that there's an invisible wall. It's that the whole idea of a wall stops making sense. Even the word outside falls apart. Because outside only means something when there's an inside to step away from and some other region to go into. So what does this really tell us? It tells us that the universe, whatever its size or shape, is self-contained. If it's infinite, it needs no beyond. If it's finite, it still needs no beyond. It doesn't hang in a bigger space. It doesn't expand into a void. It just is the arena where anything can happen. That means the question, what's beyond everything, quietly collapses. Not because there's a hidden secret, but because there's nothing there to ask about. But we don't have to stop asking questions. We just have to aim them differently. Instead of, what's outside the universe, we can ask, how did this universe begin? Instead of, where is it sitting, we can ask, how do its rules arise? Why do these laws of physics exist and not others? Instead of hunting for a physical edge, we look for the principles that make edges unnecessary. We ask how space and time themselves came to be. What conditions gave rise to them? Whether there was any kind of state before expansion, or whether before is simply a word that stops applying at some point. If space and time had a beginning, then the idea of outside might only make sense after that beginning, not before it. You need a stage before you can talk about leaving the stage, so where do we go from here? If there is no outside, and the real mystery isn't what holds the universe, but how the universe started, then the next step is to turn toward that beginning. Not outward, but inward. Not past the edge, but back toward the first moment when space, time, and everything we know began to unfold, and from there to ask a new kind of question. If there was a starting point for time itself, what does it mean for time to have an edge? When we think about edges, we usually imagine places. A fence at the edge of a yard, a shoreline at the edge of the sea, a wall at the end of a hallway. But time too raises the question of edges. Not physical boundaries, but beginnings, endings, the first moment, the final tick. And the question that follows is one of the oldest we've ever asked. Did time have a beginning? And if it did, what came before? It feels like time should stretch endlessly in both directions. After all, we experience it as a line, one we move through without choice or pause, always forward, never back. But what about behind us? Is there a point before which there was no before? In our current understanding of the universe, time does seem to have a starting point, about 13.8 billion years ago. That's when the expansion began. When space as we know it started to grow, when matter formed, when light began to move freely. That moment, the one we call the Big Bang, is often imagined as an explosion, a flash in the dark, a beginning in space, but it's not a blast that happened somewhere. It's a shift in the state of everything, and in that shift, time itself begins. There's no record of time before it, no earlier coordinates, no timeline leading up to it, not because it's hidden from us, but because as far as we can tell, it didn't exist, which brings us to a different kind of edge, not one you can reach, one you live inside, a boundary at the start of time. But if time has a beginning, what does that mean? What does it mean for something to start when there's no before? This is where the language fails us. We're used to causes and sequences, to reasons and consequences. If something begins, we want to know what made it happen, what set it off, what preceded it. But if time itself begins, then that question dissolves. There is no before the beginning of time, not because it's out of reach, but because before has no meaning without time to hold it. Some physicists think of it like a coordinate system that simply doesn't extend further. You can label time as 0 at the Big Bang and assign numbers after it. Seconds, years, billions of years. But nothing before, not because there's a wall, but because there's no axis beyond that point. Others go further. They wonder whether time is even fundamental, or if it emerges from something deeper. A more basic state where what we call time is just a way to describe change, a way to organize events but not a thing in itself. There are theories that treat the early universe as timeless, frozen but undefined, no clock, no before or after, just a set of quantum possibilities that eventually settle into a state we recognize as space and time. In those models, the Big Bang isn't a bang at all. It's a transition, a phase change, like ice melting into water, but from timelessness into history. In that view, time doesn't begin suddenly. It emerges gradually. It comes into focus as the conditions stabilize, and once it exists, it flows forward not as a rule, but as a consequence of entropy of disorder, increasing of the arrow of time, aligning with the spread of information. Still, other theories look at the possibility of a bounce, a universe that contracts before it expands. In that picture, there is a before the Big Bang, but it's not part of our time. It's part of a larger cycle, a rhythm that includes contraction, expansion, and maybe contraction again. Time loops, but space never closes. Even more radically, some ideas suggest that time could be circular, not in the way clocks are circular, but in the way paths on a curved surface eventually return. That after enough time, you find yourself not at the end but back at the beginning. None of these models are proven, but they all try to solve the same riddle. How can something begin when there was no time for it to begin? In practice, we live only in one direction. We remember the past, we influence the future. The arrow of time feels solid. But on the level of equations, in the laws of physics, time doesn't prefer one direction over another. It works forward and backward just the same. So why do we experience time as a one-way journey? Because of conditions at the beginning. The early universe was highly ordered, low entropy, smooth and hot and dense. And from that condition, disorder began to grow. Structures formed, energy spread, stars ignited, galaxies spun, information dispersed. And, with that, dispersion came the sense of time moving forward. The idea that past becomes memory and future becomes mystery. But if those initial conditions had been different, our perception of time might have been different too. Maybe we wouldn't even notice it passing. Maybe it wouldn't pass at all. Which brings us back to the edge, not as a moment to reach, but as a kind of silence, a space in which time itself waits to be born. It's not a place you can point to, not a wall, not a spark. It's more like the bottom of a well, not empty, but without direction from which time rises, like water beginning to flow. And once it flows, it changes everything. Events begin to happen. Cause and effect take shape. Particles gain motion. Light gains meaning. Expansion begins. But even that doesn't require a full stop at the start. Some models blur the beginning. They round off the singularity. They soften the edge. Time curves gently into being. No sharp line. No final barrier. Just a limit to how far we can extrapolate back. Beyond that limit, our theories break down. The equations return infinities. The models lose coherence. It's not that there's something to see before time. It's that the question stops applying, and that's not a failure of thought. It's a feature of what time is. A structure we live inside, a frame we carry with us, a thing that began not somewhere, but somehow. So when we say time has no edges, we mean it in a few ways. It may have no before, it may have no final end, and it may not be a line at all, but a shape we don't yet understand. Whatever it is, we are inside it. And if the universe has no outside, and time has no before, then maybe there are other limits to let go of. Limits not of where or when, but of what we imagine reality can be. Even if time had a starting line, it's hard not to wonder if it also has a finish line. Not just for us, not just for Earth, not just for the stars we can see, but for everything, for the fabric that holds it all, for space itself, for the flow of time we're riding right now. Could there be a last moment? A final now, after which there are no more? People have been circling that question for as long as we've been wondering how things began. If the universe switched on, could it one day switch off? And if it did, what would that mean? Does everything collapse? Does everything rip apart? Or does it just thin out and fade? Physics doesn't give us one neat answer. It offers a handful of stories, each one shaped by the same rules that brought us here. Same equations, same observations, different endings. One of the oldest endings people imagined is a kind of rewind, the Big Crunch. In that picture, gravity eventually wins. The expansion that flung galaxies apart slows down, then halts, then reverses. Space stops stretching and starts shrinking. Galaxies drift back toward one another. Distances shrink, temperatures climb. Everything that was once spread out begins to pack together again. Over unimaginable timescales, the universe would get denser, hotter, more compressed. Stars, gas, dust, dark matter, all caught in the same inward pull. The universe that once expanded from a hot, dense state would return to one, not a bang outward, but an implosion inward, a cosmic in-breath. Maybe it would end in a singularity again. Maybe in some exotic final state we don't yet have the words for, a kind of reset or a transition into something new. But as far as we can tell, that doesn't seem to be the road we're on. When we actually look, we don't see the universe slowing down. We see it speeding up. That brings us to another story. The one with the quiet name and the very long timescale, the Big Freeze. In this version, expansion never turns around. Space just keeps stretching. Galaxies keep sliding farther apart. The night sky grows emptier, not because galaxies disappear, but because they slip too far away. Stars use up their fuel and go dark. New stars form for a while, but not forever. The raw material gets used up. Star formation slows, then stops. White dwarfs, those dense stellar embers, cool down. Neutron stars sit in the dark. Black holes slowly radiate away their mass over absurdly long times. Particles may decay. Matter thins. Temperature drops closer and closer to a uniform cold. In this story, the universe doesn't crash. It runs out of things to do. Time would keep flowing. Seconds, hours, years, still stacking up. But as structure disappears and change becomes rare, time itself loses its flavor. If nothing new ever happens, later doesn't mean very much. It's just duration without events. A long, slow glide toward stillness, based on what we know right now, about dark energy, about the shape of space, about the way distant supernovas look. That quiet freeze seems like the favorite. Not guaranteed, but most likely. Still, there's another possibility. More dramatic. A version of the story where the universe doesn't just fade, it tears. This is the Big Rip. It starts with the same ingredient as the freeze. Dark energy, the thing that drives the accelerated expansion. But in a rip scenario, that effect doesn't just stay steady, it grows stronger. If the push behind expansion increases over time, then eventually it doesn't just overwhelm gravity between galaxies, it overpowers everything. First, distant galaxy clusters drift away beyond reach. Then individual galaxies start to come apart. The bonds holding them together can't compete with the stretching of space. Later, even solar systems become unstable. Planetary orbits unravel, go far enough into that future, and the stretch reaches smaller and smaller scales. Planets could be ripped apart. Molecules torn. Even atoms pulled to pieces. Space itself would be expanding so violently that nothing could stay bound to anything else. It wouldn't be a quiet dimming, it would be a staged disassembly. Far, far away, then closer. Then here. At the very end, there'd be no time left between the unbinding of one scale and the next. Just one last burst of separation, and then no structure at all. Right now, though, the math and the data don't strongly point to that fate. The acceleration we see seems steady, not wildly ramping up. The Big Rip stays on the shelf as a possible script, not the main one. There's another strange ending too. Less about stretching, more about the ground rules changing underneath everything. A vacuum decay. Right now, the vacuum of space, that empty background, might not be in its lowest possible energy state. Our universe could be sitting in a kind of false calm. Stable for a long time, but not absolutely stable. If that's true, then one day, somewhere, that vacuum could snap into a lower energy state. A tiny bubble of new physics could form. Inside that bubble, the laws of nature would be different constants, different particles, different everything. That bubble would then expand at nearly the speed of light, converting the old vacuum into the new as it goes. No warning, no build-up. No way to see it coming. From our point of view, nothing would seem strange, until, in an instant, reality as we know it is replaced, not with fire or explosion, just with something else. It sounds theatrical, but it's a serious idea in some branches of physics. Not predicted, not required, but not ruled out either. And if it happens, there's nothing we can do. No way to detect the wave before it hits, because the wave is the change. So we have a collection of endings: the crunch, the freeze, the rip, the decay. Some calm, some catastrophic, some still purely speculative. But here's the quiet fact that sits underneath all of them. None of them has happened yet. Right now, stars are still burning. Galaxies are still spiraling. Matter is still forming patterns. Light is still crossing the gaps between things. We live in a very particular slice of cosmic time, not at the violent beginning, not at the silent end. Somewhere in the middle, while the universe is bright and busy. That alone is remarkable. Even if the universe goes on for unfathomable eons after us, even if time stretches forward without a final tick, we don't go on forever. Our bodies don't. Our species might not. Our little window of awareness is short compared to the life of stars, let alone the life of the cosmos. So when we wonder about the end of time, we're really holding two questions at once. Will the universe ever stop changing? And long before that, what does it mean that we are here now, thinking about it? Because even if time never hits a wall, our part in its story is a brief, delicate chapter, a small, bright moment in a universe that may one day freeze, or fade, or transform into something we can't yet imagine. You don't usually think of it this way, but you spend your whole life brushing up against infinity, not as poetry, just as how things are built. Every second that slides past you is one link in a chain that, as far as we know, doesn't come with a final link attached. Time just keeps offering another moment, and another, and another. When you measure the distance from your hand to the wall, or from your pillow to the door, you're using a scale that you could, in principle, slice thinner and thinner forever. Half the distance, then half again, then half of that. No matter how small the gap gets, the idea of halfway never runs out. You don't have to leave Earth or ride a rocket into deep space to touch the infinite. It's already built into the quiet, ordinary things around you. Think of a simple pencil line on a piece of paper. It has a clear length. You could put a ruler beside it and say, it's this long. But mathematically, that same line is bottomless. Between any 2 points on it, there's another point, and between those two, another. You can zoom in forever, and you never arrive at a final dot, a last indivisible speck, where the line stops being a line. Time seems to work that way too. Between two beats of your heart, there's room for more moments. Between the tick and the next tick on a clock, there's still in between. The clock just chops time into convenient chunks for you. It doesn't mean time itself is chunked. As far as our best descriptions go, time flows continuously. Like a smooth film, not a stack of frames. Space and time, the things we think of as huge and cosmic, are also secretly hiding in every tiny movement you make. The length of your arm reaching for a glass, the path your eyes follow across the ceiling, the tiny pause between one breath and the next. Each of those is sitting inside a continuum that refuses to bottom out. No smallest step, no smallest slice. That's why infinity isn't just a fancy word in a textbook. It's baked into the way we describe reality. You might never know if the universe is infinite in size. You might never see the edge of the observable cosmos, let alone beyond it. But when you pick up a ruler, you're already holding a scale that has no built-in stopping point. When you check the time, you're already participating in a flow that, at least in our equations, has no smallest click. You're embedded in something that stretches without a clear end in both directions. Outward into distance, inward into detail. Even when we talk about very small, very finite things, infinity sneaks in through the back door. Take a single grain of sand. It looks tiny, almost nothing. But inside that grain are more atoms than you could realistically count, even if you spent your whole life doing nothing else. Take a little cube of the air around your face. Inside it, trillions of particles are zipping and colliding and shifting trajectories constantly. Every breath you take depends on an absurd number of tiny interactions. Every step, every blink, every quiet adjustment your body makes without telling you. You live inside oceans of detail too deep to list, and yet you move through them as if they were just air or sand or floor. The infinite isn't some cold, unreachable ocean at the edge of the universe. It's the water you're already standing in. Even when we try to keep things tidy and finite, we lean on infinity to do it. A fixed volume of space, say, your room, can be modeled as a continuous spread of points. There's a wall over there, but between here and there, the grid never runs out of coordinates. A short span of time, say, the minute you've been listening, can be treated as containing infinitely many instants. A simple shape, like a square or a circle, is defined using relationships between lines and curves that themselves rest on an underlying continuum. To measure a square, you imagine an invisible grid that could be refined forever. To measure a second, you imagine slicing it down into smaller and smaller pieces. Our tools for understanding reality, rulers, clocks, coordinates, equations, almost all assume that between any 2 points, there's always something in between. And it's not just physics. Your mind itself is very good at wandering into infinity. As soon as you really understand that numbers don't stop, that after any number you name, there's always +1, you've stepped into an endless staircase. 2, 3, 10, 100, a million, a trillion, and then you realize you can just keep going. There is no last, counting number hiding somewhere in the distance. However high you climb, there's always one more step. Children notice this pretty early. They'll ask, what's the biggest number? And they try to invent one, a million, a zillion, something they can trap infinity inside. And the quiet answer is, you can't. That's the whole point. There's always another. There is no final lid you can put on how many. Space has a similar habit. You can zoom down from a person to an organ, to a cell, to a molecule, to an atom, to smaller pieces still. Our models keep finding structure inside structure. We haven't found a final, smallest thing that refuses to be split further. Some theories suggest there might be a limit, a tiny scale where our idea of distance itself stops making sense, often called the Planck length. But even that is more like a question mark than a hard wall. It may just be where our current theories stop working, not where reality stops being detailed. If there's no true fundamental pixel of space or time, no last unit, then infinity isn't just a property of the very large, it's also a property of the very small. You can see the same idea hiding in the constants we use every day without thinking about them. Draw a circle, and its circumference is related to its diameter by pi, a number whose decimal expansion never repeats, never ends. Computer speed, and you're dividing one continuum, distance by another, time. Use a phone, send a message, light a screen, and you're triggering processes that depend on vast numbers of particles and the continuous fields they move through. You don't see those infinities directly, but they're there in the background math that makes everything work. So, the infinite really isn't far away. You don't have to picture every galaxy or stare into the deepest parts of space to meet it. It's woven into every coordinate you write down, every second that passes, every line, every circle, every smooth motion you make. Every one of those things contains more detail than you could ever finish unpacking, more structure than you could ever fully count, more in between than you could ever pin down. And if you sit with that for a moment, something curious happens. The usual question starts to flip. Instead of wondering, how far away is infinity, you start to wonder, how is anything ever finished? How can anything be completely measured or completely known if the framework it lives in keeps going and going and going without a natural edge? Maybe that's part of why the big cosmic questions keep pulling at us. We're not just drawn to the size of the universe out there, we're noticing the same pattern inside ordinary things. The infinity of space isn't just in distant galaxies, it's hidden in the gap between your hands. The infinity of time isn't just in the age of the cosmos. It's in the pause between two thoughts. The infinity of possibilities isn't just in multiverse theories, it's in the way one question always unfolds into another question, and then another. We never see the whole of infinity at once. We never hold it in our heads. But it's quietly present in every moment, every place, every number that refuses to end neatly. And once you realize you're already surrounded by it, the universe stops feeling like just a big room you're trying to map. It starts to feel like something else, not just a place, but a structure, a set of deep rules and patterns that run on and on. Whether you're looking at galaxies or grains of dust, or the length of your own breath, if the universe is in some sense a structure, a kind of thought running on its own rules, then here's a softer, stranger idea to sit with. You are part of that thought, not separate from it, not standing outside, looking in, but a local pattern in the same system. A brief configuration of matter and energy and information that for a while is arranged in such a way that it asks questions about itself. From the universe point of view, if it had one, you're not an intruder. You're one of its ways of briefly paying attention to itself. Your brain, right now, lying wherever you are, is a piece of physical hardware shaped by gravity and chemistry and time. But it's also something more abstract, a shifting pattern of signals, constantly updating, constantly rewriting itself. Neurons firing, strengthening some connections, weakening others. Electrical activity weaving through a network that quietly encodes your memories, your habits, your sense of self. That pattern is made of information. And that information is constrained by rules, by physics, by biology, by the geometry of space-time, by whatever the deepest level of reality turns out to be. You're not outside those rules. You are those rules in a particular arrangement. Which means that when you lie there wondering whether the universe has an edge, or whether time will end, or whether reality is more like a thought than a thing, the question itself is part of the structure. The curve of the question, the way it unfolds, the feelings it stirs, that's all just more of the universe expressing its logic in a temporary local form called you. The edge you're probing is partly out there and partly in here, because edges aren't only distances. They can also be limits of understanding, limits of perception, limits of what a finite mind can hold at once. You bump into those edges all the time. You reach the limit of your vision when the room goes dark, the limit of your attention when your thoughts start to blur, the limit of your day when your body nudges you towards sleep. The air. The limit of your day when your body nudges you towards sleep. From inside your mind, those limits can feel like the boundaries of the world itself. When something is beyond your reach, it's easy to imagine there's nothing there, that the unknown is empty. But as we've seen, the universe doesn't necessarily end where your perception stops. The observable universe ends where light runs out of time to reach you. But beyond that, more space almost certainly continues. In the same way, your ability to think about infinity ends at a certain point. Your working memory fills, your intuitions stall. But beyond that mental horizon, the structure you're trying to describe doesn't suddenly vanish. Your understanding ends. The pattern you adjust can't stretch that far in one piece. And that's all right, because if reality really is structured like a thought, a system of rules and relationships, then no single mind is supposed to hold the whole thing at once. Just like no single cell understands the body, and no single galaxy knows the universe, your mind is one small local pattern, doing what patterns do, following the rules available to it, exploring a tiny neighborhood in an endless space of possibilities. So when you wonder about edges, maybe what you're really feeling is the edge of your own capacity. The mind wants things to be finite. It wants a center, and a boundary, and a clear outside. It wants the universe to behave like a room, or a book, or a map, something you can hold all at once. But the deeper you look, the more that picture starts to bend. A universe without a center, time without a clean beginning or end, you can picture. Space that might be finite but unbounded, or infinite but never fully knowable. Rules that look less like machine parts and more like abstract symmetries, mathematical constraints, flows of information. It all sounds very far away, but you're built from the same ingredients. The same logic that governs galaxies also governs the atoms in your fingertips, the signals in your brain, the patterns of your breathing as it slowly deepens. The same equations that describe light crossing intergalactic space also describe light bouncing off the walls of your room, landing softly on your closed eyelids. You're not separate from the thought. You're a sentence in it, a sentence that, for a little while, gets to ask, what kind of story am I in? And maybe that's what makes questions about infinity and edges feel so strangely emotional. They're not just intellectual puzzles. They're about where you fit in the structure. Whether there's a wall around you, or whether you're floating in something that doesn't end. If the universe is a thought, a structure, a system of logic playing itself out, then you're a little temporary subroutine, a small process running, exploring, branching, and eventually stopping. And when your process ends, the larger structure goes on. The rules remain. The pattern of reality keeps unfolding. The thought continues. That might sound lonely at first, but it doesn't have to be. It can also feel strangely comforting. Because if reality really is rooted in structure, and not just stuff, then nothing is ever entirely lost. The particular configuration that is you won't repeat in exactly the same way. That's part of what makes you, you. But the fundamental rules, the deep symmetries, the underlying logic that allowed you to exist at all, those are built into the fabric. You're a brief local way that the universe tried out a question about itself. You asked about edges. You asked about infinity. You asked what it means for a universe to be real, or for a life to be small inside something so large. And the asking itself is already an answer of a kind. It means the structure is rich enough, subtle enough, intricate enough to produce beings who can wonder, beings who can take a few moments, like this one, to trace out the shape of questions they'll never fully solve, and still feel a kind of calm in the trying. In a logic-based universe, not every statement needs to be closed. Some lines can remain open-ended. Some proofs never finish. Some questions stay questions. You don't have to solve infinity to fall asleep next to it. You don't have to find the edge of the universe to be safely inside it. You don't have to understand every rule to be carried by them. Right now, as you listen, the same structure that governs the drift of distant galaxies is also quietly handling the tilt of your head on the pillow, the slow rhythm of your breath, the way your muscles loosen when you let them. The same space that might be infinite is also the space between your thoughts as they soften and spread out. And all those edges you've been thinking about, the edge of the universe, the edge of the observable, the edge of time, fade for a while into a different kind of edge. The edge of sleep. On one side, there's clear, waking thought, full of questions and models and images of balloons and hyperspheres and infinite lines. On the other side, there's dream logic, where structure relaxes, where time bends, where edges blur and reform in softer ways. You're standing right at that boundary now, feeling the world of sharp questions loosen into something gentler. The universe will keep expanding whether you're awake to calculate it or not. Infinity will remain infinite whether you're there to imagine it or not. The great thought, whatever it truly is, will go on thinking itself. You, for tonight, don't have to. You're allowed to let the big questions drift to the edges of your awareness, like distant galaxies sliding past the horizon. You're allowed to keep only a faint impression of them, a feeling that you live in something vast and logical and mysterious, and that your life somehow fits inside that pattern, perfectly, just as it is. No edges required, no final answers needed. Just you, here, a temporary pattern in a quiet universe, letting your own thoughts slow, letting your own internal structure soften, letting the rules of sleep take over, where the rules of cosmology leave off. Whenever you're ready, you can let this question go. Let it dissolve like starlight redshifting into the background. Let your attention narrow from the size of the universe to the size of your own breath. In, out. The cosmos can handle itself for a while. You can rest. As you lie there now, you don't have to hold any of this anymore. Not infinity, not edges, not questions. You don't even have to hold yourself quite so tightly. Let your thoughts wander the way light does, outward, softer, thinner, until they fade into the background. They don't need to be tidy. They don't need to be finished. They can just drift. If you like, you can notice 3 small things right here, right now. The feeling of where your body touches what's supporting you. The weight of your eyelids, even if they're still a little open. The gentle rise and fall of your breath, arriving and leaving all on its own. That's enough universe to be responsible for tonight. Somewhere, galaxies are colliding. Somewhere, stars are being born. Somewhere, space is stretching itself a little thinner. And somewhere very specific, right where you are, everything is allowed to be simple. Just warmth, just gravity, just breathing. If a thought about infinity comes back, that's okay. Let it pass through like a comet, bright for a moment, then gone beyond the horizon. You don't need to chase it. You don't need to understand it. You've already walked all the way to the edge of the question and gently looked over. From here on, you can just rest. So we'll leave you in this quiet pocket between seconds, between heartbeats, between one day and the next. The universe will keep doing what it does. You don't have to. Sleep if you like, drift if you like, dream if you like, and whenever you find your way back, tomorrow, next week, next lifetime of curiosity, we'll be right here again, at the edge of another question, waiting to wander through it with you.